Imagine for a moment that you could reach back through time and touch the very first light that ever shone in our universe. Not the light from the first stars, not the glow of infant galaxies, but something far older, far more primordial. This light has been traveling for over 13 billion years, carrying with it the secrets of creation itself, and it's still washing over us today. It's called the cosmic microwave background radiation, and it's not just some faint echo from the past. It's a cosmic fingerprint left behind from the Big Bang, and it holds clues about everything: how the universe began, how it grew, and perhaps even how it will end. For decades, we've looked at this ancient glow and thought we understood it, but what if we've been missing something hidden in plain sight? What you're about to discover is that the cosmic microwave background is so much more than a static snapshot of the infant cosmos. It's a dynamic, a rich, and deeply mysterious treasure map, one that's still being decoded. Recent breakthroughs have revealed subtle patterns, strange irregularities, and whispers of physics beyond our current understanding, all buried within this microwave static. What if some of the most fundamental assumptions we've made about the universe are incomplete, or even wrong because we overlooked crucial details in this primordial light? That's the possibility that's now stirring excitement, debate, and profound curiosity among cosmologists around the world. In this video, we're going to embark on a journey to explore what we might have missed in the microwave. We'll travel from the serendipitous discovery of the cosmic microwave background by two astronomers who initially thought their signal was caused by pigeon droppings, to the cutting-edge missions scanning the skies with never-before-seen precision. We'll dive into anomalies that challenge our models, from the so-called axis of evil that hints at a preferred direction in the cosmos, to the enigmatic cold spot that might be evidence of something stranger than we ever imagined. You'll see how questions about inflation, dark flow, and even the multiverse are all tied to the subtle patterns in this ancient light. So come with us. This is not just a story about science, but about human curiosity, perseverance, and our endless desire to understand where we came from and what lies beyond. Now, let's rewind the cosmic clock back to the year 1964. At the legendary Bell Labs in Homedale, New Jersey, two young radio astronomers named Penzias and Wilson were wrestling with a problem. They were using a massive, exquisitely sensitive horn antenna, originally built for satellite communication, to study radio emissions from the Milky Way. But no matter where they pointed this giant instrument, they were plagued by a persistent, maddening hiss, a uniform, static noise that seemed to come from every direction in the sky. It was always there, day and night, season after season. They were meticulous scientists, so they went to incredible lengths to eliminate this interference. They checked and rechecked their electronics. They pointed the antenna toward New York City, thinking it might be some form of urban radio pollution. They even suspected the actual physical instrument itself. Famously, they discovered a pair of pigeons had taken up residence inside the large horn, and they had decorated the interior. Convinced this white dielectric material, as they politely called it, might be causing the noise, they evicted the pigeons and scrubbed the entire assembly clean. And yet the hiss remained. It was a signal that refused to go away, an uninvited guest in their data that would ultimately turn out to be the most important discovery in modern cosmology. This stubborn noise was, of course, the cosmic microwave background radiation. But Penzias and Wilson didn't know that yet. They were simply frustrated, unable to explain this anomaly in their work. The breakthrough came through a chance conversation. Penzias happened to call a fellow radio astronomer, Bernard Burke, who mentioned that he'd just heard about a preprint paper by a team at Princeton University, led by the physicist Robert Dicke. Dicke's group was actively building a radio antenna with one specific, ambitious goal: to find the leftover radiation from a theoretical hot, dense beginning of the universe, the Big Bang. They had predicted that if such an event had occurred, the entire cosmos should be filled with a faint, cool glow of microwave radiation, cooled down over billions of years from its initial searing heat. When Penzias heard this, it was the ultimate eureka moment. He later recalled the profound realization, saying something to the effect of, they had been trying to get rid of the very signal another team was desperately trying to find. Their annoying background noise wasn't a flaw, it was the echo of creation itself. They quickly contacted the Princeton group, and the two teams published companion papers in the Astrophysical Journal in 1965. Penzias and Wilson's paper, humbly titled, A Measurement of Excess Antenna Temperature at 4080 MHz, simply described the mysterious signal, while Dicke's team interpreted it as the relic radiation from the Big Bang. This accidental discovery was nothing short of a revolution. It catapulted the Big Bang theory from being one competing idea among others into the foundational model of our universe. It provided the first direct, observational evidence that the universe had a definite beginning in a hot, dense state. For this monumental achievement, Penzias and Wilson were awarded the Nobel Prize in Physics in 1978. But what exactly were they detecting? To understand its significance, we have to travel back even further in time, to a period roughly 380,000 years after the Big Bang. Before this moment, the universe was an opaque, searing plasma soup, so hot that electrons and protons couldn't combine to form atoms. Light particles, or photons, were constantly bouncing off these free electrons, trapped in a chaotic dance, unable to travel any meaningful distance. The universe was a brilliant, blinding fog, but as the cosmos expanded, it cooled. At that critical threshold of about 3000 degrees Celsius, electrons finally slowed down enough to be captured by protons, forming the first neutral hydrogen atoms. In an instant, the fog lifted. The photons, suddenly freed from their constant collisions, could now stream across the universe unimpeded. That first flash of light, released from every point in space, has been traveling ever since, stretched and cooled by the relentless expansion of the universe over the next 13.8 billion years. What Penzias and Wilson detected with their horn antenna was that very light, redshifted from visible waves into the microwave part of the spectrum, now just a faint whisper only a few degrees above absolute zero. They were, in the most literal sense, listening to the birth cry of the cosmos. This discovery didn't just answer a question, it opened up an entirely new field of study, giving us our very first baby picture of the universe and establishing the cosmic microwave background as the single most important piece of data we have for understanding our cosmic origins. With this incredible discovery in hand, the scientific community was electrified, but a new challenge immediately presented itself. The initial measurements from Penzias and Wilson, while groundbreaking, only told part of the story. They showed that the cosmic background radiation was remarkably uniform, coming from every direction with the same intensity. This near-perfect uniformity was a stunning confirmation of the Big Bang, but it also created a profound puzzle. If the early universe was so incredibly smooth and featureless, how did it ever evolve into the complex, lumpy cosmos we see today, filled with galaxies, stars, and planets? The answer, it turned out, was hidden in the tiniest of details, imperfections so small that they were completely invisible to the first generation of instruments. This led to the development of a powerful theoretical framework, one that sought to explain the universe's large-scale structure and evolution. Scientists began to interpret the CMB's smoothness as evidence for a perfect blackbody spectrum, the signature of an object in complete thermal equilibrium. This observation strongly supported the cosmological principle, the idea that on the largest scales, the universe is both homogeneous, meaning it looks the same at every point, and isotropic, meaning it looks the same in every direction. It was a beautiful, elegant picture of a simple and orderly cosmos. This initial interpretation gave rise to what would become the standard model of cosmology, a robust set of ideas that seemed to explain almost everything. But this model, in its elegant simplicity, was built on an assumption that the universe could be described by straightforward, clean physics. It was a necessary starting point, a foundation upon which to build, but it was perhaps a little too confident, a little too sure that it had captured the entire cosmic story in a single, neat package. The quest to test this elegant picture demanded a new level of precision. That quest was answered by one of the most ambitious scientific missions of the 20th century, the Cosmic Background Explorer, or COB Satellite. Launched by NASA in November of 1989, COB was designed with one supreme goal: to measure the cosmic microwave background with an accuracy that was simply impossible from the Earth's surface, free from the interference of our atmosphere. For years, the satellite collected data, and the scientific world waited with bated breath. The initial results were both a triumph and a revelation. First, COB instruments confirmed with exquisite detail that the CMB was indeed a near-perfect blackbody, its spectrum matching theoretical predictions with an astonishing precision. It was, as the Nobel Committee would later say, the shape of the universe itself. But COB's second finding was even more transformative. When the team, led by the legendary George Smoot, finally produced a full sky map of the CMB's temperature, they didn't find a featureless, flat plane. Instead, they discovered a breathtaking tapestry of tiny variations, minute fluctuations in temperature on the order of 1 part in 100,000. These weren't errors, they were cosmic seeds. Smoot famously announced that looking at the map was like seeing the face of God. But for cosmologists, it was more like seeing the blueprint for the entire universe. These tiny ripples in the fabric of space-time were the gravitational wells into which matter would eventually fall, serving as the primordial nuclei for everything: the great cosmic voids, the massive clusters of galaxies, and ultimately the stars and planets we call home. Armed with this new, rich data from COB and later missions, the standard model of cosmology rapidly evolved into its modern form, known as the Lambda cold dark matter model, or Lambda CDM. This mouthful of a name actually tells a profound story. Lambda represents the cosmological constant, a mathematical term Albert Einstein once called his greatest blunder, which we now understand as dark energy, the mysterious force responsible for the accelerating expansion of the universe. Cold dark matter refers to the invisible, unknown type of matter that does not interact with light, but whose gravitational pull is 5 times stronger than that of normal matter, acting as the cosmic scaffolding upon which galaxies are built. The Lambda CDM model was spectacularly successful. It could reproduce the large-scale structure of the universe, explain the precise ratios of light elements forged in the Big Bang, and account for the observed rate of cosmic expansion. It became the triumphant, reigning paradigm, a testament to human ingenuity in deciphering the cosmos. Yet, in its very success lay a potential blind spot. The model's parameters were finely tuned to fit the beautiful, smooth data from COB, which had a resolution that, while revolutionary for its time, was still relatively coarse. It saw the universe in broad brushstrokes. In their drive to build a coherent and comprehensive model, scientists necessarily made simplifications. They assumed that the primordial universe was governed by Gaussian, random fluctuations, a statistical term meaning the patterns were essentially simple and predictable. They operated under the comfortable assumption that the cosmological principle held absolutely true, that there were no preferred directions or strange, large-scale asymmetries. The model was a masterpiece of explaining what we could see, but it wasn't particularly equipped to go looking for things we hadn't even thought to imagine. It was a map that confidently charted the known lands but left the edges blank, with no notation of "here be dragons." This early confidence, while crucial for progress, may have inadvertently caused us to overlook subtle complexities, faint whispers in the data that didn't fit the simple narrative. We were so focused on confirming the grand, sweeping story of the cosmos that we might have missed the intriguing footnotes, the anomalous clues hidden within the microwave static that were patiently waiting for a more sensitive ear to listen. But as our instruments grew sharper, peering deeper into this cosmic fossil record, a new and more puzzling picture began to emerge. The universe, it turned out, was not quite as perfectly uniform as we had once believed. Hidden within that near-perfect smoothness were tiny, strange, and deeply intriguing imperfections, statistical quirks in the data that stubbornly refused to fit neatly into our standard model. These are what cosmologists call anomalies, and they are the first compelling hints that our understanding of the cosmos might be missing a crucial piece of the puzzle. Imagine looking at a vast, seemingly flawless sheet of ancient parchment, only to discover upon closer inspection a series of faint, unexpected wrinkles and creases that don't align with the main text. These aren't random smudges, they feel intentional, like a secret message or a clue left behind by the author. That is precisely what missions designed to succeed COB began to find etched into the fabric of the cosmic microwave background. The first major leap forward came with the Wilkinson Microwave Anisotropy Probe, or WMAP, launched in 2001. Where COB map was a beautiful but blurry impressionist painting, WMAP provided a crystal-clear high-definition image. It measured the temperature fluctuations across the entire sky with a resolution over 30 times finer than its predecessor. Scientists eagerly awaited this new, detailed map, expecting it to be the final confirmation of the Lambda CDM model, smoothing out any remaining uncertainties. And for the most part, it was a resounding success, precisely measuring key cosmological parameters with an accuracy of just a few percent. But it also did something else. It revealed with startling clarity that the universe has a slight but noticeable preference. The fluctuations on one side of the sky appeared to be ever so slightly larger and more pronounced than on the opposite side. Furthermore, the alignment of these fluctuations seemed to suggest a peculiar kind of asymmetry, a preferred axis that ran through the cosmos. This was deeply unsettling. The foundational cosmological principle, the bedrock of modern cosmology, states that the universe should have no preferred direction. It should look the same everywhere. Yet here was data from one of the most precise scientific instruments ever built, suggesting that on the largest scales, the universe might not be isotropic after all. It was as if we had discovered that the fundamental canvas of reality was ever so slightly tilted. Then, in 2009, the European Space Agency's Planck satellite took to the skies, representing the absolute pinnacle of CMB observation. With sensitivity so profound it could detect temperature variations of a millionth of a degree, Planck was tasked with creating the ultimate map of the infant universe. If WMAP provided a high-definition image, Planck's map was an ultra-high-resolution, scientifically calibrated masterpiece. The scientific community held its breath, hoping Planck would resolve these strange anomalies, showing them to be mere artifacts of earlier, less precise measurements. But the opposite happened. Planck didn't smooth over the wrinkles. It revealed them in even greater, more confounding detail. It confirmed the large-scale asymmetry WMAP had seen. It also mapped an enigmatic and profoundly cold region in the southern sky, a vast area significantly chillier than its surroundings that became famously known as the cold spot. This wasn't a tiny blip. It was a colossal cosmic bruise, a region of space so anomalously cold that it defied easy explanation. Other oddities appeared in the data, such as a curious lack of correlation in the temperature fluctuations at the very largest angles, something the standard model predicted should be there. The reaction from the cosmology community was a fascinating mix of intense excitement and rigorous skepticism. Researchers like Professor Joanna Dunkley of the University of Oxford have often urged caution, rightly pointing out that the human brain is a pattern recognition machine that can easily find significance in random statistical noise. The history of science is littered with discoveries that vanished under closer scrutiny. The rigorous process involves running countless simulations of the universe based on the standard model to see how often these peculiar features appear just by chance. Sometimes they do, but the most persistent anomalies, like the large-scale asymmetry and the cold spot, have proven to be unusually stubborn, appearing in the data again and again, even as our analysis techniques improve. This puts scientists in a delicate position. They are not claiming to have overthrown the standard model, far from it. The model remains incredibly successful. Instead, they are acknowledging that these anomalies are like a faint, persistent tapping at the door of our understanding. They are unresolved questions, potential clues that we might be on the verge of something far grander and more complex than we ever imagined. They are the cosmic equivalent of a detective finding a single, unexplained fingerprint at a crime scene that otherwise seems open and shut. It doesn't prove the case is wrong, but it absolutely demands a closer look because it might just be the key to a much deeper truth. Of all the strange features found in the cosmic microwave background, perhaps none is more provocatively named or philosophically troubling than the so-called axis of evil. This isn't a title dreamed up for a science fiction blockbuster. It's the very real nickname scientists have given to a bizarre and persistent alignment in the sky that seems to defy one of our most sacred cosmological rules. To understand why this is so shocking, we have to go back to that foundational idea, the cosmological principle. For centuries, this has been a guiding light for astronomy, stating that the universe is isotropic. It should look the same in every direction, with no special place or preferred orientation. There should be no up or down in the cosmos, no left or right on a universal scale. It's a beautiful, democratic idea that places no one location above any other. The axis of evil challenges this notion at its core, suggesting that the universe might in fact have a tilt, a preferred axis, almost like a hidden compass needle pointing toward something we cannot see. The story of its discovery begins with the incredibly detailed full sky maps produced by the WMAP satellite. When cosmologists analyzed the patterns of hot and cold spots in the CMB, they weren't just looking for random arrangements. They were performing complex statistical tests to see if the fluctuations were truly random and evenly distributed as the standard model predicted. To their growing astonishment, they found that the largest scale fluctuations, the biggest ripples in the fabric of spacetime, were not randomly oriented. Instead, they appeared to be aligned along a specific axis that stretches across the sky, from the constellation Virgo to the opposite point near the constellation Eridanus. It was as if the universe had subtly brushed its primordial hair in one particular direction, leaving a faint but detectable part in the cosmos. This wasn't a small-scale effect. This was a signature written across the entire observable universe. The most unsettling part, this axis, this purported preferred direction, also seems to be eerily aligned with the plane of our own solar system and the direction in which we are moving through space. This immediately raises the terrifying possibility for a scientist that what we're seeing isn't a feature of the universe at all, but merely a reflection of our own local environment, a contamination of the pristine primordial signal by something much closer to home. Naturally, the first assumption was that this had to be an error, a systematic flaw in the WMAP data processing or an unaccounted for foreground effect. The scientific process is built on such healthy skepticism, so when the more advanced Planck satellite was launched, one of its key missions was to check this bizarre result with even greater precision and better control over potential sources of error. The cosmology community waited, expecting Planck to be the arbiter that would finally smooth over this embarrassing wrinkle and restore order to our cosmic maps. But Planck did no such thing. In fact, it confirmed the anomaly. The alignment was still there, staring back at scientists from the most precise measurements of the early universe ever made. The axis of evil had not been vanquished by better technology. It had been reinforced. This was the moment it transformed from a curious statistical fluke into a genuine cosmological puzzle. The implications of this are profound enough that they have elicited strong reactions from some of the field's most prominent figures. Cosmologist Lawrence Krauss has been famously blunt about it, calling the existence of such an alignment embarrassing for the standard model. He wasn't saying the model is wrong, but rather that this is a glaringly obvious problem that remains frustratingly unresolved, an anomaly that sits in the living room of cosmology that we have to explain or explain away. It creates a deep tension between our elegant theories and our stubborn observations. If the universe truly has a preferred axis, it forces us to reconsider everything from the initial conditions of the Big Bang to the fundamental nature of the inflation that followed. Perhaps inflation wasn't perfectly uniform, stretching space in a slightly different way along one direction. Or perhaps it points to something even more exotic, like the influence of another universe beyond our own, exerting a gravitational pull on our cosmic bubble. The very name, Axis of Evil, playfully captures this sense of a fundamental threat. It's a nod to a political phrase from the time of its discovery, but in a scientific context, it represents an anomaly that could undermine the very evil of a perfectly random, isotropic universe. This isn't just an abstract problem for theorists to debate. It's a powerful lesson in the nature of scientific progress. The history of science is not a straight line of accumulating facts. It is a story of anomalies forcing paradigm shifts. The orbit of Mercury didn't quite match Newton's predictions, and that tiny anomaly was a clue that eventually led Einstein to his theory of general relativity. The axis of evil represents a similar modern-day clue. It may not overthrow our entire understanding of the cosmos, but it absolutely demands a re-evaluation of our assumptions. It forces us to ask uncomfortable questions. Have we been too quick to accept a simplified version of the universe? Are we missing a crucial piece of physics that would account for this large-scale structure? This single anomaly, this cosmic compass pointing toward the unknown, is a brilliant reminder that our maps of the universe are still works in progress, and the most exciting discoveries often lie in the places where the map reads, "Here there be dragons." If the axis of evil makes cosmologists a little uncomfortable, then the cold spot is the anomaly that keeps them up at night. Picture the most detailed map of the cosmic microwave background, a sphere of subtle temperature variations rendered in a palette of blues and reds. Across most of this map, the fluctuations are small and random, a placid sea of primordial ripples. But then, in the southern galactic hemisphere, nestled in the constellation Eridanus, your eye is drawn to a vast, deep blue patch. This is the cold spot. It's not just a little cooler than its surroundings. It's a profound and jarringly large depression in temperature, spanning 1 billion light-years across. It's as if you were looking at a beautifully smooth sheet of ice and found one massive, sprawling crack. This isn't a subtle statistical quirk. It's a glaring feature that feels like it demands an explanation far beyond the ordinary. When it was first identified in the WMAP data and later confirmed with even greater clarity by Planck, the immediate, most straightforward hypothesis was that it might be a shadow. The leading theory proposed that this cold region could be caused by an immense cosmic void, a staggering underdensity in the distribution of galaxies, a truly empty place in the universe. The physics behind this is known as the integrated Sachs-Wolf effect. In simple terms, as light from the CMB travels through the universe, it gains or loses a tiny amount of energy when passing through gravitational wells and hills. Climbing out of a deep gravitational well, like a massive cluster of galaxies, costs the photon energy, making it appear slightly cooler or redshifted. Conversely, if a photon travels through a vast, mostly empty region of space, a void where the gravitational potential is shallower, it doesn't lose as much energy. As a result, when it exits the void, it actually has more energy relative to the average, making it appear warmer. But wait, that would make a void a hotspot, not a cold one. This is where the expansion of the universe comes in. In a universe dominated by dark energy, the gravitational potentials of these large structures are not static, they decay over time. This subtle change imparts an additional secondary energy shift to the photons. For a supervoid, this secondary effect can actually dominate, causing the CMB light that passes through it to lose a net amount of energy, creating a cold imprint on the sky. So the hunt was on. Astronomers embarked on massive spectroscopic surveys, painstakingly mapping the three-dimensional distribution of galaxies in the direction of the cold spot, searching for the supposed supervoid that would solve the mystery. The results of this search have been deeply ambiguous, fueling the debate rather than settling it. Some surveys did indeed find evidence of a large underdense region in that part of the sky. However, the size and emptiness of this void, while significant, simply didn't seem to be nearly vast or profound enough to account for the staggering coldness observed in the CMB. The numbers just didn't add up. The predicted effect was too weak. It was like finding a small pothole on a road and trying to blame it for the massive sinkhole that had swallowed a truck. This discrepancy led researchers like Professor Tom Shanks at the University of Durham to question the void explanation altogether. His team's analysis of galaxy data suggested that the underdensity in that region might be even less significant than previously thought, perhaps no greater than would be expected by chance in the cosmic web. If there's no gargantuan void to blame, then what in the universe could have left such a massive and frigid bruise on the fabric of reality? This is where the explanations venture from the unlikely into the truly spectacular. When the conventional answer fails, science must turn to the unconventional, and the cold spot has inspired some breathtakingly exotic theories. One of the most fascinating possibilities is that it could be the imprint of a collision with another universe. This idea emerges from the multiverse concept predicted by some models of eternal inflation. In this vast cosmic landscape, our universe might be just one bubble among countless others, all inflating in a greater meta-universe. Occasionally, these bubbles might collide. If a neighboring universe had bumped into ours in the distant past before the CMB was released, the energy released at the boundary of that collision could have created a vast, localized disturbance in the fabric of spacetime. This disturbance would then leave a specific, circular signature on the CMB, a spot that is noticeably colder than the surrounding area. the cold spot size and temperature profile make it a compelling, if highly speculative, candidate for such a cosmic crash site. It's a literally universe-shattering idea, suggesting that our entire cosmos is not an isolated island but part of a far vaster and more strange archipelago of realities. Other theoretical physicists have proposed equally mind-bending origins rooted in the exotic physics of the very early universe. One such idea involves objects or defects known as cosmic textures. Textures are hypothetical knots in the fields that permeate space, formed during a phase transition in the primordial universe, a fraction of a second after the Big Bang. Think of it like the flaws that form in ice as water freezes. As the universe cooled and its fundamental forces separated, imperfections could have been locked into the structure of space-time itself. If one of these textures later unraveled, it would have released an immense amount of energy, creating a powerful gravitational shockwave that would leave a very specific signature on the CMB, a circular cold spot surrounded by a hot ring. The cold spot's profile has been studied to see if it matches this prediction, and while it's a compelling match for some, the evidence remains inconclusive. The ongoing debate between the supervoid hypothesis, the cosmic texture model, and the multiverse collision idea is a beautiful example of science in action. It's not a chaotic free-for-all. It's a rigorous process of making predictions, gathering new data, and letting the evidence slowly guide us toward the truth, no matter how strange that truth may be. The cold spot stands as a monument to our ignorance, a cosmic puzzle that reminds us that the most profound discoveries often begin with an anomaly that refuses to go away. While the temperature maps of the cosmic microwave background revealed the stunning blueprint for all cosmic structure, they were only telling us half the story, perhaps even less. To truly understand the violent birth of our universe, we had to learn to read its hidden language, a language not written in heat, but in the very direction of the light waves themselves. This is the story of polarization, a subtle property of light that has opened an entirely new window onto the cosmos, offering us a chance to peer back into the first fleeting instance of time, to a period so brief and energetic it defies comprehension. Light, at its most fundamental, is an electromagnetic wave. We often visualize it as a wave vibrating in all directions, like a rope being shaken wildly. But when light is scattered or emitted under certain conditions, those vibrations can become organized, preferring a specific plane. This preferred direction of vibration is what physicists call polarization. It's a phenomenon we encounter in everyday life. Polarized sunglasses work by blocking the horizontally polarized glare reflected off a road or water, allowing only the vertically polarized light to pass through and reducing strain on our eyes. The ancient light of the CMB is also polarized, and for a deeply profound reason. Remember that moment of recombination, when electrons and protons combine to form the first atoms and set the photons free. That final interaction, that last scatter, imprinted a specific polarization pattern on the light, a pattern that has been traveling through the expanding universe ever since. It's a fossilized record of the very last thing that happened to that light before its 13 billion-year journey began. Cosmologists categorize these faint polarization patterns in the microwave background into two distinct types, which they poetically call E modes and B modes. The names come from an analogy with electromagnetism, referring to patterns that have specific curl-free E for electric or curl-B for magnetic properties. While the names are technical, the distinction is crucial. The more common E-mode polarization is primarily generated by the density fluctuations in the primordial plasma, the same lumps and bumps that created the hot and cold spots in the temperature map. They are essentially a different view of the same cosmic blueprint, caused by the simple motion of electrons scattering photons in the hot, early universe. They are incredibly important, but they largely tell us about the universe a few 100,000 years after the Big Bang. The real Holy Grail, the signal that has driven a generation of experimentalists to build ever more sensitive telescopes in some of the most remote and hostile environments on Earth, is the B-mode polarization. B-modes are different. They are the fingerprint of something far more dramatic. Gravitational waves rippling through the fabric of space-time itself from the inflationary epoch. To understand why this is so revolutionary, we need to revisit inflation, the theory that proposes the universe underwent a period of exponentially rapid expansion in the first fraction of a second after the Big Bang. This theory elegantly solves several major cosmological puzzles, but direct, smoking gun evidence for it has been elusive. According to the theory, the violent energy of inflation would have shaken the very foundations of reality, creating powerful ripples in space-time primordial gravitational waves. Unlike the E-modes, which are created by scalar density perturbations, these tensor perturbations, the gravitational waves, would have a unique twisting effect on the light, imprinting a distinct B-mode pattern on the CMB polarization. Detecting this signal would be nothing short of monumental. It wouldn't just confirm that inflation happened, it would tell us about the energy scale at which it occurred, opening a direct portal to physics at energies 1 trillion times higher than what we can achieve in the largest particle colliders. It would be our first ever observational clue about quantum gravity, a glimpse into the realm where Einstein's theory of gravity and quantum mechanics must finally meet. The pursuit of this signal has been one of the most dramatic and challenging quests in modern science. The excitement reached a fever pitch in March of 2014, when the team behind the BICEP 2 telescope, located at the South Pole, announced they had detected the telltale swirls of B-mode polarization. The announcement was met with global headlines and a wave of euphoria in the scientific community. It felt like a Nobel Prize-winning moment. However, that euphoria was short-lived. The BICEP 2 team had made a critical and heartbreaking error. They had indeed detected polarization, but it wasn't from the primordial universe. It was foreground contamination, specifically polarized dust within our own Milky Way galaxy. Interstellar dust grains, aligned by the galaxy's magnetic field, can also polarize light and produce a B-mode signal that looks eerily similar to the one cosmologists are desperately searching for. The celebration turned into a masterclass in scientific rigor and collaboration. The BICEP 2 team joined forces with the COB Satellite team, which had precisely mapped this galactic dust across the entire sky. The combined analysis revealed that the signal could be entirely explained by this local interference. It was a sobering lesson in the immense difficulty of this search. This challenge perfectly illustrates the analogy of trying to read a desperately faded ancient manuscript. The primordial B-mode signal we seek is the faint, almost invisible ink of the original text. The foreground contamination from our galaxy is like later scribbles, coffee stains, and water damage that have been scrawled over the top of it. Our task is to use every tool at our disposal, multiple frequencies of observation, sophisticated statistical models, and incredibly sensitive instruments, to carefully separate the original cosmic text from the local graffiti. This painstaking work continues today with projects like the BICEP/Keck Array, the Simons Observatory, and the Future Light Bird Satellite, all designed with the specific goal of distinguishing the incredibly faint whisper of inflation from the roar of the Milky Way. The fact that this subtle signal was completely invisible to the first generations of CMB telescopes tells us that the story of the microwave background is far from over. With each technological leap, we are developing new ways to see, allowing us to extract layers of information that were once thought lost to noise, bringing us closer than ever to reading the universe's very first diary entry. Imagine trying to listen for a single, faint whisper in a crowded, roaring stadium. That is the essential, monumental challenge facing every cosmologist who studies the cosmic microwave background. We are not simply pointing a telescope at a clean, empty patch of sky to receive a pure signal from the dawn of time. Instead, we are trying to isolate that ancient whisper from a cacophony of modern cosmic noise. Our own Milky Way galaxy, along with countless other galaxies and sources between us and the edge of the observable universe, are all broadcasting their own signals, blaring their own stories right on top of the one we're desperate to hear. This interference is what scientists call foreground contamination, and it is arguably the single greatest practical obstacle in the quest to understand the primordial universe. It's a problem so pervasive that every single feature we see in the CMB maps from missions like Planck and WMAP has to be scrutinized with one critical question. Is this a real feature from the Big Bang, or is it just galactic static? The sources of this contamination are varied, persistent, and incredibly good at mimicking the signal we're after. One of the most significant culprits is simple, everyday interstellar dust. But this isn't the dust you find on a bookshelf. This is cosmic dust, microscopic grains of carbon and silicate forged in the hearts of ancient stars and scattered across the galaxy. These tiny particles, though cold by earthly standards, are still much warmer than the frigid 3-degree Kelvin background of the CMB. Because of this, they glow with their own thermal emission, primarily in the infrared and microwave parts of the spectrum. But the real problem isn't just their glow, it's that these dust grains are not randomly oriented. The Milky Way's magnetic field causes them to spin and align, and this alignment polarizes the light they emit. As we learned in the quest for primordial B modes, this polarized dust emission is a perfect counterfeit for the inflationary signal we seek, a malicious cosmic forger working right in our own backyard. Then there's synchrotron radiation, a phenomenon that sounds like science fiction but is a dominant feature of our galactic neighborhood. This is the intense, polarized light generated when high-energy electrons, accelerated to nearly the speed of light by supernova remnants or the galaxy's magnetic field, spiral around magnetic field lines. It's the same physical process that creates the brilliant radio lobes of distant quasars, but it's happening throughout the plane of our own galaxy, creating a pervasive, foggy glow that shines brightly at the lower microwave frequencies where we also observe the CMB. And the contamination doesn't stop there. There's free emission caused by electrons scattering off ions in the hot, diffuse gas of the interstellar medium. There's even emission from spinning nanoparticles of dust, a more recently identified contributor. And beyond our galaxy, there are the faint but cumulative radio emissions from all the distant galaxies in the universe, a background hum known as the cosmic infrared background. Each of these sources has its own unique spectral signature. The way its intensity changes across different frequencies, but they all overlap, creating a messy, tangled web of interference that completely obscures the pristine CMB signal. So how do we possibly untangle this mess? The key lies in a fundamental property of light that distinguishes the imposters from the real thing. The true cosmic microwave background has a perfect blackbody spectrum. This means its intensity across different frequencies follows a very specific, smooth curve predicted by fundamental physics. The foreground contaminants do not. Synchrotron radiation, for instance, gets much brighter at lower frequencies and fades away at higher ones. Dust emission does the opposite, becoming more prominent at higher frequencies. This difference is the master key. Missions like Planck were not equipped with a single microwave camera. They were marvels of engineering, carrying a suite of instruments that observed the sky simultaneously at 9 different frequencies, from 30 GHz to 957 GHz. By taking these 9 different pictures of the sky, each one dominated by a different mix of foregrounds and the CMB, cosmologists can act like master restorers of a priceless painting. They use sophisticated statistical algorithms to build detailed models of the dust, the synchrotron radiation, and the other contaminants based on their known spectral behavior. Then they subtract these modeled foregrounds from the total observed signal at each point in the sky. What is left behind, in theory, is the clean, uncontaminated light from the universe's infancy. This process, known as component separation, is as much an art as it is a science, and it is fraught with peril. The entire endeavor rests on the accuracy of our models of these foregrounds. If our understanding of how galactic dust polarizes light is even slightly incorrect, or if there are unknown sources of contamination we haven't accounted for, then the subtraction process will be flawed. The consequences are twofold, and both are deeply troubling. First, an imperfect subtraction could leave behind residual foreground features that we then mistakenly interpret as genuine primordial anomalies. A clump of unusual dust or a patch of turbulent synchrotron radiation could be misread as a cold spot or a strange alignment, sending theorists down years of fruitless pursuit of new physics that doesn't exist. This is a very real concern that leading researchers constantly grapple with. As one Planck collaboration scientist famously cautioned, "The most dangerous thing in cosmology is your own galaxy." The foregrounds are a minefield, and a single misstep in the data processing can create a spectacular false positive. But the opposite problem is perhaps even more insidious and often less discussed. What if our overzealous cleaning doesn't leave behind false signals, but instead scrubs away real ones? The process of component separation is necessarily aggressive. To be sure you're removing all the contamination, you might inadvertently subtract a faint, subtle, but genuine feature of the CMB itself. If there is a large-scale, unexpected pattern in the primordial light that doesn't fit our preconceived notions of what the CMB should look like, our standard foreground models might mistakenly identify it as noise and eliminate it. We could be digitally erasing the very clues we're searching for, ironing out the wrinkles of the universe in our quest for a clean dataset. This creates a profound philosophical dilemma. How do we search for the unexpected when our primary tool for seeing clearly is designed based on what we already expect to see? It forces a constant re-evaluation of the methods themselves. As data from new, more powerful observatories like the Simons Observatory rolls in, a significant portion of the scientific effort will not be on analyzing the CMB itself, but on rigorously cross-checking and validating the ever more complex foreground models. The quest to hear the universe's first whisper is in large part a quest to understand the acoustics of the entire concert hall we're sitting in. It's a meticulous, painstaking process that reminds us that what we might have missed in the microwave isn't just buried in the data. It might have been accidentally deleted by our own best efforts to see it clearly. To solve these profound mysteries of the early universe, cosmologists needed a theory that was both incredibly powerful and elegantly simple. They found it in a concept known as cosmic inflation. This idea proposes that a fraction of a second after the Big Bang, somewhere around 10 to the power of -36 seconds, the universe wasn't just expanding, it was undergoing a period of hyper-driven, exponential growth, inflating from a subatomic speck to something approaching the size of a grapefruit in an almost unimaginably brief flash. This sudden, violent stretching of spacetime itself provides elegant solutions to some of the most stubborn puzzles left by the standard Big Bang model. The most famous of these is the horizon problem. When we look at the cosmic microwave background, we see that it is almost perfectly uniform, with the same temperature in all directions to within 1 part in 100,000. But according to the classic Big Bang timeline, these regions on opposite sides of the sky were never in causal contact. There hasn't been enough time since the beginning for light or heat to travel between them to even out their temperature. It's like walking into a large room and finding that every single person has the exact same body temperature to a fraction of a degree, even though they all just arrived from different, isolated towns and never communicated. How could they possibly have coordinated that? Inflation solves this by suggesting that the entire observable universe was, in fact, once a tiny, microscopic region that was in perfect thermal equilibrium. This tiny patch was then stretched by inflation to become larger than the entire cosmos we can see today. Those opposite sides of the sky were once neighbors, close enough to share a uniform temperature before being dramatically wrenched apart. The uniformity we see is simply a fossil of that initial, intimate connection. Beyond solving the horizon problem, inflation also provides a beautiful and compelling origin story for the cosmic structures we see all around us. The theory posits that the driving force behind this explosive expansion was a hypothetical field permeating space called the inflaton field. Like any quantum field, the inflaton would have been subject to tiny, unavoidable quantum fluctuations, brief, random flickers of energy popping in and out of existence. The genius of inflation is that it takes these microscopic quantum jitters and, in the act of rapidly stretching space-time, magnifies them to astronomical proportions. These minuscule density fluctuations were blown up to become the seeds of all future structure, the gravitational wells that would eventually attract matter to form galaxies, clusters, and the vast cosmic web. This process makes a very specific prediction about the kind of pattern these seeds should leave imprinted on the cosmic microwave background. It predicts that the distribution of hot and cold spots should be almost, but not perfectly, scale invariant. This means that the fluctuations should have roughly the same amplitude or strength, regardless of their size on the sky. Whether you're looking at a tiny ripple or a giant wave in the CMB, the theory suggests they should have a similar magnitude. This is a profound prediction, and when the COB, WMAP, and Planck satellites mapped the CMB, they found a spectrum of fluctuations that matched this inflationary prediction with stunning accuracy. It was a monumental triumph, solidifying inflation as the leading paradigm for the very beginning of our universe. However, the story doesn't end with this success. While the broad brushstrokes of the CMB align perfectly with a simple, single-field model of inflation, the devil, as always, is in the details. As our maps have become exquisitely precise, cosmologists have begun to scrutinize the finer statistical properties of these fluctuations, looking for subtle deviations from the simplest predictions. And they have found some intriguing, persistent hints that the full story of inflation might be more complex and richer than we first imagined. One of the most significant of these statistical anomalies is the curious lack of large angle correlations. The standard inflationary model predicts a specific level of correlation, or similarity, between temperature fluctuations that are separated by very wide angles on the sky over 60 degrees or more. Yet, when scientists analyze the data from both WMAP and Planck, they find that these largest-scale fluctuations are noticeably less correlated than the theory says they should be. It's as if the universe is missing some of its biggest possible waves, making the largest scales appear slightly smoother and more bland than our models anticipate. This isn't a small discrepancy. It's a feature that has persisted across different satellites and different data analysis techniques, and it sits at a confidence level that makes it very difficult to dismiss as mere chance. This anomaly, along with others like the hemispheric asymmetry and the cold spot, forces us to ask a critical question: does this mean inflation is wrong? The answer is almost certainly no. The theory's core successes are too great to discard. A more compelling possibility is that we are seeing the first hints that the inflationary epoch was not a simple, smooth, single-event process driven by one solitary field. Perhaps the inflattened field had help. Theorists have proposed models involving multiple inflattened fields interacting with each other, creating a more dynamic and complex early universe. In such a scenario, the transition at the end of inflation could have been messier, leaving behind imprints that subtly alter the statistical properties of the CMB on the very largest scales. Other exotic ideas suggest that the initial conditions for inflation were not perfectly uniform, or that the physics governing the inflattened field itself is more intricate, involving features that create localized effects in the primordial power spectrum. Each of these possibilities would predict a different statistical signature, a different pattern of deviations from perfect scale invariance. The large angle correlation anomaly, therefore, isn't a refutation of inflation, it's a potential clue. It's a whisper from the dawn of time suggesting that the inflationary universe was a more interesting, more complicated, and more fertile place than our simplest models describe. By carefully studying these statistical wrinkles in the microwave background, we are not just testing a theory, we are beginning to write a detailed biography of the universe's first fleeting moments, a story that appears to be far more fascinating than we ever dreamed. But what if the answers to these cosmic riddles don't lie within our universe at all? What if the key to understanding the cold spot, the axis of evil, and the other strange features in the microwave background requires us to step outside our cosmic bubble and contemplate a reality so vast it defies all intuition? This brings us to perhaps the most spectacular and mind-bending idea in all of modern cosmology, the multiverse. According to some of our most promising theories, particularly those involving eternal inflation, our entire universe might not be the entirety of existence. Instead, it could be just one single bubble in a frothing, infinite cosmic sea, one reality among a potentially infinite number of others, each with its own unique laws of physics, constants, and perhaps even dimensions. This isn't just science fiction, it's a serious, though highly speculative, extension of our best physical models. And if this multiverse is real, the collisions between these budding universes in the greater meta-universe could have left permanent scars on the oldest light we can see, turning the cosmic microwave background into a potential bulletin board for messages from other realities. The theoretical mechanism is as fascinating as it is complex. In the eternal inflation scenario, the vacuum energy that drove our universe's brief inflationary period is not a one-time event. It's a perpetual state of affairs in a much larger background reality. In this hyper-dynamic environment, quantum fluctuations continuously spawn new pocket universes, each inflating into its own separate cosmos, disconnected from all the others. Think of it as a pot of water coming to a rolling boil, with new bubbles constantly forming, expanding, and rising to the surface. Now, imagine what happens when two of these bubbles, expanding at nearly the speed of light, are born too close together. Before they can inflate away from each other and lose causal contact, their edges might actually collide. This collision would be a cataclysmic event, releasing an immense amount of energy at the boundary. For a universe like ours, still in its infancy and incredibly hot and dense, such a collision would send a powerful shockwave rippling through the primordial plasma. This shockwave would create a localized disturbance in the density and temperature of the universe, a kind of cosmic bruise, and when that universe cooled down and released its first light, the CMB, that bruise would be frozen in time, imprinted on the sky as a distinct circular pattern. It wouldn't look like a simple cold spot. According to the models, a genuine bubble collision would likely appear as a series of concentric rings with a specific temperature profile, a series of alternating hot and cold rings, a target like bullseye on the cosmic microwave sky. This is where the cold spot comes roaring back into the conversation. For some theorists, its large, amorphous, and profoundly cold nature makes it a compelling, if imperfect, candidate for the remnant of such a collision. Proponents of this idea, like theoretical physicist Laura Mersini-Horton, have pointed to the cold spot and other large-scale anomalies, such as the mysterious alignment of the axis of evil, as potential evidence that our universe did not develop in perfect isolation. She and others have argued that the gravitational pull from a neighboring universe, or the aftereffects of a near-miss collision, could have exerted an influence on the distribution of matter and energy in our early cosmos, creating these persistent asymmetries that so confound the standard model of cosmology. Mersini-Horton has stated that these features could be the smoking gun, evidence that our universe is part of a much larger multiverse, a claim that is as bold as it is controversial within the wider physics community. It is crucial to emphasize that this remains a highly speculative frontier of science. Despite extensive searches through the Planck data and other datasets, no definitive, unambiguous evidence of a bubble collision like a perfect set of concentric rings has ever been found. The cold spot, while strange, does not perfectly match the predicted profile for a collision remnant. Many cosmologists maintain a healthy skepticism, arguing quite reasonably that extraordinary claims require extraordinary evidence, and that we should exhaust every possible explanation within our own universe before invoking the fantastical idea of others. The controversy is a vital part of the scientific process, a necessary tension between imaginative theoretical exploration and rigorous empirical validation. Yet, the very fact that we can use our most precise map of the primordial universe to even test such an astounding idea is a testament to how far we've come. The cosmic microwave background, that faint whisper from the dawn of time, has become our most powerful telescope, not just for looking back into our own beginning, but for potentially peering across the unimaginable void into the realms beyond. It serves as the ultimate testing ground, challenging us to ask the most profound questions we can muster about the nature of reality itself. Just when we thought the cosmic mysteries couldn't get any deeper, another profound enigma emerges from the data, one that suggests the entire observable universe might be caught in a vast, unseen current. This phenomenon is known as dark flow, and it represents one of the most unsettling and controversial findings in modern cosmology. Imagine throwing a handful of leaves into a gently flowing river. They all drift together in the same general direction, carried by a current you can't see but whose effects are undeniable. Now scale that image up to a cosmic proportion. Astronomers, by meticulously studying the motion of massive galaxy clusters, have found evidence that these colossal structures aren't just moving apart due to the expansion of the universe. They also share a subtle, coordinated, and persistent drift in the same direction, as if they are all being gently tugged by a gravitational force originating from far beyond the edge of everything we can see. The method for detecting this motion is as ingenious as the finding itself, and it brings us right back to the cosmic microwave background. We are all familiar with the Doppler effect, the way a siren's pitch seems to change as it moves toward or away from us. The same principle applies to light. When an object moves toward us, its light is compressed, shifting it toward the blue end of the spectrum. When it moves away, the light is stretched, shifting it toward red. This is how we measure the velocity of stars and galaxies. But there's another, more subtle Doppler effect imprinted on the CMB itself, because our solar system is moving relative to the rest frame of the cosmic microwave background. The sky doesn't appear perfectly uniform to us. The light coming from the direction we're moving toward appears very slightly warmer or blue-shifted, while the light from the direction we're moving away from appears very slightly cooler or redshifted. This creates a dipole anisotropy, a hot pole and a cold pole in the CMB map. By measuring this dipole, scientists can calculate our precise motion through the cosmos. We know, for instance, that our Milky Way galaxy is hurtling toward the Great Centaurus cluster at a staggering 600 kilometers per second. This established fact becomes the baseline for an even more profound investigation. The question then becomes, are the galaxy clusters around us also moving relative to the CMB rest frame in a random, haphazard way, or is there a larger pattern? To find out, a team led by astronomer Alexander Kashlinsky at NASA, a Goddard Space Flight Center, employed a clever technique. They used the hot, X-ray emitting gas within distant galaxy clusters as a tracer. The movement of a cluster through the CMB creates a specific and measurable distortion in the CMB's temperature in that spot, known as the kinematic Sunyaev-Zeldovich effect. In simple terms, the CMB photons get a slight energy boost when they scatter off the hot electrons in a cluster that is moving toward us, and they lose a bit of energy when scattering off a cluster moving away. By carefully analyzing data from the WMAP and Planck satellites for hundreds of clusters out to billions of light-years away, Kashlinsky's team made a startling claim. They found evidence that these clusters were not just moving randomly. Instead, they reported a consistent, coherent flow, a dark flow, of hundreds of clusters all moving in the same direction toward the constellations Centaurus and Hydra at velocities of nearly 1,000 kilometers per second. And this flow seemed to be detected at distances so vast that it shouldn't be possible according to our standard model of cosmology. The gravitational influence of all the known matter in the observable universe simply isn't strong enough or structured enough to create such a coordinated motion on such an immense scale. The implications of this, if true, are nothing short of revolutionary. The standard cosmological model is built on the assumption that the universe is homogeneous and isotropic on the largest scales, meaning there should be no preferred direction and no structures large enough to exert a gravitational pull beyond a certain point. The observable universe is, by definition, the portion of the cosmos from which light has had time to reach us since the Big Bang. Nothing from beyond that cosmic horizon can possibly affect us, as no information can travel faster than light. Dark flow directly challenges this. A coordinated motion on this scale suggests that these galaxy clusters are being influenced by the gravitational tug of something truly enormous that lies outside our observable bubble. It could be a concentration of mass on a scale we can scarcely imagine, a supercluster of galaxies, or something even more exotic, whose gravitational reach extends into our visible universe, pulling everything toward it. Some theorists have even speculated that it could be evidence of another universe in the multiverse, a neighboring cosmic bubble whose mass is gravitationally interacting with our own in a way that leaves this faint directional imprint. It's a concept that pushes the boundaries of physics and philosophy, suggesting that our entire cosmic neighborhood might be just a small part of a much larger and mostly hidden structure. Unsurprisingly, a finding of this magnitude has been met with intense scrutiny and vigorous debate. The central question is one of statistical significance and the elimination of systematic errors. Other research teams have attempted to replicate the analysis, often using different methodologies or data sets, and have arrived at contradictory conclusions. Some studies have failed to find any evidence of a coherent flow beyond what is expected from known large-scale structures within our observable universe. Critics argue that the detected signal could be an artifact of imperfect foreground subtraction. Perhaps the glow of our own galaxy or other local emissions were not completely removed from the CMB maps, creating a false dipole signal that mimics a bulk flow. Others point to the challenges of accurately measuring the velocities of such distant clusters and the potential for subtle biases to creep into the complex statistical analysis. The debate is a classic example of science at the frontier, where extraordinary claims are rightly subjected to extraordinary levels of skepticism and require multiple, independent lines of evidence to be widely accepted. Through this heated debate, Alexander Kashlinsky has remained a steadfast advocate for the phenomenon and the need for further investigation. He acknowledges the criticisms but argues that the signal has persisted through multiple analyses and data releases, growing stronger rather than vanishing. He contends that dismissing it as a systematic error is too easy an answer, and that scientists have a responsibility to pursue such puzzling anomalies, especially when they point to potentially profound new physics. The quest to confirm or refute dark flow continues with new catalogues of galaxy clusters and more sensitive all-sky surveys. Each new data set provides a fresh opportunity to test this tantalizing hypothesis. Whether dark flow is ultimately confirmed as a real cosmological phenomenon or relegated to the history books as a fascinating statistical fluke, its investigation has already served a crucial purpose. It has demonstrated once again that the cosmic microwave background is not an isolated relic, but is deeply connected to the dynamics of the entire cosmos. It forces us to confront the humbling possibility that what we see and measure might be just a small part of a much grander and still hidden cosmic story, where unseen forces from beyond the horizon are quietly shaping the fate of everything we know. This growing list of cosmic curiosities, from the axis of evil to the enigmatic cold spot, isn't just a collection of isolated oddities. They are, in fact, deeply connected to one of the most pressing and urgent problems in all of modern cosmology, a disagreement so fundamental it has been dubbed the Hubble tension. At its heart, this is a crisis of measurement, a dispute over a single, critical number, the Hubble constant. This number represents the current expansion rate of our universe, the speed at which galaxies are receding from us. Knowing this value is akin to having a master key for cosmology. It tells us the age of the universe, its size, and its ultimate fate. For decades, we believed we were homing in on a precise, agreed-upon value. But then, our two most trusted methods for measuring it began to return stubbornly different answers, creating a rift that has only widened with each new, more precise observation. It's as if we built two incredibly accurate clocks to measure cosmic time, but they are ticking at undeniably different speeds, and no one can figure out why. The first method for telling this cosmic time looks back, way back, to the earliest possible epoch we can observe, the cosmic microwave background. The CMB is our ultimate early universe anchor. By meticulously analyzing the subtle patterns of hot and cold spots in this primordial light, specifically the size and distribution of these ripples, cosmologists can deduce the physical conditions of the infant cosmos with incredible precision. These conditions, the amount of normal matter, and dark energy, along with the geometry of the universe, are all intricately linked through the equations of our standard cosmological model to predict how fast the universe should be expanding today. It's a bit like examining the detailed blueprint of a grand clock as it was being built, and then using your knowledge of physics and mechanics to predict exactly how fast its hands will be moving billions of years later. This approach, using data from the Planck satellite, gives us a very precise answer for the Hubble constant, approximately 67 kilometers per second per megaparsec. This means that for every megaparsec, a staggering 3.26 million light-years of distance, a galaxy is moving away from us 67 kilometers per second faster. The second method for telling time is far more local and direct. Instead of reading ancient blueprints, this technique uses what astronomers call the distance ladder. It involves measuring the expansion rate by observing objects whose distances and velocities we can measure directly in the present-day universe. The most important rungs on this ladder are Cepheids variable stars and Type Ia supernova. Cepheids are stars that pulse with a regularity that is directly tied to their intrinsic brightness. By measuring their pulse rate, we know their true brightness. Comparing that to how bright they appear from Earth gives us a precise distance. Type Ia supernova are even more powerful. They are thermonuclear explosions of white dwarf stars that all reach nearly the same peak brightness, making them brilliant standard candles visible across vast cosmic distances. By carefully measuring the redshifts and distances to these objects, teams like the one led by Nobel laureate Adam Rees have painstakingly built a measurement of the Hubble constant that is completely independent of any model of the early universe. Their result is unequivocal and has been confirmed repeatedly. The universe is expanding at about 73 kilometers per second per megaparsec. At first glance, a difference between 67 and 73 might not seem like much, but in the world of precision cosmology, where error bars have been squeezed to within an inch of their lives, this 6-kilometer gap is a yawning chasm. The discrepancy is now at a confidence level of 5 sigma, meaning there is only a 1 in a million chance that it's a random fluke. This isn't a minor calibration error. It is a fundamental disagreement about the current state of our universe. One of our most trusted clocks, built from the primordial echo of the Big Bang, says one thing. Another, built from the brilliant fireworks of dying stars in our cosmic neighborhood, says another. They cannot both be right. This is the Hubble tension, and it strongly suggests that something is missing from our equations, that our standard model of cosmology, the Lambda CDM model, is incomplete. The most exciting possibility is that this tension is not an error but a clue, a direct pointer to new physics waiting to be discovered. Cosmologists are now exploring a fascinating menu of potential solutions, each more dramatic than the last. One leading candidate is an early form of dark energy. Our current model only includes dark energy as a recent actor, dominating the expansion in the last few billion years. But what if an additional, exotic form of energy was also active in the universe's first few 100,000 years? This early dark energy would have subtly altered the rate of expansion just before the CMB was released, changing the size of the sound waves frozen into its pattern. This would mean we've been slightly misreading the Planck blueprint, leading to an incorrect prediction for the present-day expansion rate. Other theories propose modifications to Einstein's theory of gravity itself on the largest scales, or new types of dark matter that interact in strange ways. Some even suggest that our local region of the universe is slightly underdense, a local void, making our nearby measurements unrepresentative of the cosmos as a whole, though this is generally considered a less likely explanation. What makes the Hubble tension so powerful is its direct connection back to the anomalies in the CMB. Many of these proposed solutions to the tension would leave their own distinct fingerprints on the primordial microwave background. For instance, a model involving early dark energy might also predict a specific alteration to the large angle polarization patterns or amplify certain statistical anomalies. This means the CMB isn't just the source of one side of the argument, it is also the testing ground for the solutions. next-generation telescopes like the Roman Space Telescope and the Vera C. Rubin Observatory will attack the distance ladder with unprecedented precision, while future CMB missions will scour the ancient light for the subtle imprints of these new physics. The Hubble tension has transformed from a technical disagreement into a guiding light, compelling us to re-examine every assumption and explore every corner of our theories. It proves that the universe is still full of surprises, and that the most profound discoveries often begin not with a bang, but with a stubborn, perplexing disagreement between two of our most trusted instruments. Yet for all its theoretical promise, the actual detection of these primordial B-modes has proven to be one of the most formidable technical challenges ever undertaken in observational astronomy. The signal we are trying to find is almost impossibly faint. We are not looking for a bold, obvious swirl on the map. We are searching for a pattern of polarization whose amplitude is predicted to be more than 1,000,000 times weaker than the temperature fluctuations in the CMB. To put that in perspective, it's like trying to measure the thickness of a sheet of paper from a distance of 60 miles, or listening for the faint rustle of a single leaf in the middle of a hurricane. This unimaginable faintness means that every single component of the telescopes built for this search must operate at the very bleeding edge of physics and engineering. The detectors themselves are miracles of nanotechnology, tiny arrays of superconducting sensors cooled to a fraction of a degree above absolute zero, capable of detecting the minuscule energy deposited by a single photon. But even these are not enough. The entire instrument must be shielded from any form of interference. It must be placed in locations that are among the most pristine on Earth, high on the cold, dry Antarctic plateau where the atmosphere is thin and stable, or even launched into the frigid silence of space. And even then, the most insidious enemy is not the environment, but the instrument itself. The tiniest imperfection in a lens, a minute amount of stray heat, a microscopic misalignment in the cryogenic coolers, any of these systematic errors can produce a false signal that perfectly mimics the cosmic one we so desperately seek. Controlling for these effects is a painstaking, years-long process of calibration and recalibration, a relentless pursuit of perfection where 99.9% just isn't good enough. This immense challenge is being met by a global collaboration of scientists working on a series of increasingly ambitious experiments, each one building on the lessons and often the heartbreaks of the last. The story of the BICEP array at the South Pole is a perfect example of this iterative, communal nature of science. The initial BICEP 2 announcement in 2014 was a seismic event in cosmology, a moment of pure, unadulterated excitement that seemed to mark the end of the quest. But it was the rigorous, collaborative work that followed that truly embodies the scientific spirit. The team's willingness to work with their colleagues on the Planck mission to cross-check their findings against a galactic dust map, and then to publicly acknowledge that their signal was contamination, was not a failure. It was a masterpiece of professional integrity and a powerful lesson in humility. That experience directly informed the design of the next generation of the experiment, the BICEP/Keck array. These telescopes no longer look at a single frequency. They observe across multiple frequencies simultaneously, precisely so they can characterize and subtract the polarized emission from galactic dust, the very thing that had led them astray. This multi-frequency approach is now the gold standard, employed by other ground-based projects like the Simons Array in Chile and the massive Simons Observatory, also under construction in the Atacama Desert. These projects represent a scaling up of effort, using thousands of detectors instead of hundreds to cover more sky with greater sensitivity. And looking further ahead, space-based missions like Japan's LightBird satellite are in development. designed to escape Earth's atmosphere entirely and conduct a full-sky, multi-frequency survey free from any terrestrial interference. This entire decades-long endeavor is a testament to the fact that monumental discoveries are rarely made in a single, dramatic leap. They are more often the product of a slow, careful, and collective crawl, a process where each null result and every dead end is just as valuable as a potential success. This last point is crucial to understanding the true nature of this scientific quest. In the popular imagination, a null result, a failure to detect the thing you're looking for, is often seen as a disappointment, a wasted effort. In the rigorous world of cosmology, it is exactly the opposite. Each time an experiment like BICEP/Keck or the South Pole Telescope publishes new results that push the upper limit on the strength of the primordial B-mode signal even lower, they are not admitting defeat. They are actively ruling out entire families of theoretical models. They are telling the theorists, your beautiful idea that predicted a strong signal from a high-energy version of inflation. That one can't be right. These ever-tightening constraints are powerful tools that force a refinement of our ideas. They funnel theorists away from dead ends and toward models that are more nuanced, more complex, and often more interesting. As one researcher involved in the search often says, we are not just chasing a signal, we are mapping the void. We are defining the space in which the true answer must lie. This painstaking process of elimination is what ultimately transforms a wild frontier of speculation into a precise science. The fact that we have not yet definitively detected primordial gravitational waves does not mean the search has been for nothing. It means we have been meticulously drawing a map of what inflation is not, and with each passing year, that map becomes more detailed, guiding us ever closer to the truth that must be hidden within it. The subtle signals we might have missed in the first, coarse maps of the microwave sky were never going to be easy to find. Their discovery demands more than just better technology. It requires a profound depth of patience, a resilience in the face of setback, and an unwavering commitment to the slow, iterative, and deeply collaborative process of discovery. Up until now, we've been talking about the universe's structure in terms of size and temperature, the amplitude of the hot and cold spots. But there's an even deeper layer of information encoded in the cosmic microwave background, one that deals not with the strength of the fluctuations, but with their arrangement, their relationships to one another. This brings us to one of the most technically complex but profoundly important concepts in modern cosmology, non-gaussianity. At its heart, it's a question about the very randomness of the primordial universe. The standard story of inflation paints a picture of a process driven by a single, simple quantum field, the inflaton, whose random jitters were stretched across the sky to create the seeds of all structure. In this simple, elegant model, the distribution of these hot and cold spots should follow what statisticians call a Gaussian or normal distribution. You can picture this as a classic bell curve. Most of the fluctuations would be of average size with fewer very hot and very cold spots, and their arrangement on the sky would be essentially random, with no special patterns or correlations between them. This Gaussian signature is the statistical fingerprint of a simple, serene birth for the cosmos. But what if the infant universe was a more chaotic, more interactive place? This is where non-gaussianity comes in. The term refers to any deviation from this perfect, random, bell curve distribution. It would mean that the hot and cold spots in the CMB are not completely independent of each other, that there are hidden correlations, subtle patterns that suggest the fluctuations were not born from a simple, quiet quantum process, but from something more dynamic and complex. Finding strong non-gaussianity would be like looking at a vast field of snow where most footprints are random. but then discovering a set of tracks that move in pairs or a path that curves in a specific way. These patterns would tell a story of interactions that the simple model simply doesn't account for. They would be the statistical smoke pointing to a very different kind of fire in the early universe. To understand what these patterns might look like, cosmologists have developed specific technical ways to search for them. They don't just look at individual hot and cold spots. They look at the relationships between 3 points at a time, a complex analysis called the bispectrum. Within this, they search for particular shapes or configurations that different physical processes would imprint. For instance, some models predict a squeezed configuration, where 2 points are very close together and the third is very far away. This specific shape is a key prediction of certain multi-field inflation models, where more than one quantum field was active during the explosive expansion. The interaction between these fields could create a situation where a very large-scale fluctuation, a vast wave in space-time, modulates the smaller, local fluctuations within it, creating a correlated pattern across vastly different scales. Finding this would be direct evidence that inflation was not a solo act, but a complex duet or even a full orchestra of fields working in concert. Another telling pattern is the equilateral configuration, where all 3 points form roughly the same distance from each other. This shape is often associated with models where the inflattened field interacts with itself in non-trivial ways, or with theories that involve exotic physics like higher dimensional effects. Each different shape in this statistical zoo points a finger at a different culprit behind the universe's birth. Perhaps one of the most thrilling sources of non-gaussianity isn't from a field at all, but from a cosmic defect. Theorists have long proposed the existence of one-dimensional cracks in the fabric of spacetime called cosmic strings. These are not strings in the everyday sense, but incredibly dense, ultra-thin filaments of energy left over from a phase transition in the very early universe, thinner than a proton but with the mass of a mountain range per inch. As these strings move through the primordial plasma, they would create sharp, linear disturbances, ripples in spacetime that would leave a very specific, non-Gaussian signature in the CMB. Unlike the subtle statistical patterns of multi-field inflation, the signature of a cosmic string would be a clear, dramatic discontinuity, a straight line etched across the map of the ancient sky. Finding evidence for cosmic strings would be a monumental discovery, providing a direct window into physics at energy scales 1 trillion times higher than what we can probe in any particle collider. So, what have we found after years of painstaking analysis with Planck and other data? Thus far, the universe has been remarkably, and some might say frustratingly, Gaussian. The search for these exotic statistical fingerprints has so far come up empty, or more precisely, has placed incredibly tight constraints on any possible non-Gaussianity. The fluctuations in the CMB are, for all intents and purposes, consistent with pure randomness. For proponents of the simplest inflationary models, this is a resounding victory, a confirmation of their elegant and minimalistic approach. But for many theorists, this null result is not the end of the story. It's a powerful guide. The fact that we have not found strong non-Gaussianity has already allowed us to rule out entire classes of inflationary models. Grand, elaborate theories that predicted a rich and obvious non-Gaussian signal have been effectively falsified by the exquisite data from Planck. This process of elimination is a crucial, if less glamorous, part of the scientific journey. It forces theorists to refine their ideas, to develop more nuanced models that can explain the profound simplicity we observe while still accounting for the other anomalies we've discussed. The search for non-Gaussianity exemplifies a deeper truth about cosmology. Sometimes what we don't find is just as important as what we do. The stunning randomness of the primordial universe is itself a profound clue, pushing us toward ever more refined and subtle theories of how everything began. But as we peel back the layers of the cosmic onion, we find that the universe is not just made of matter and energy, but is also threaded through with invisible lines of force that could hold their own secrets. We are surrounded by magnetic fields. Our planet has one protecting us from solar winds. Our sun has a powerful one driving sunspot cycles and solar flares. Even our entire galaxy, the Milky Way, is permeated by a vast, though weak, magnetic field that guides cosmic rays and aligns interstellar dust. For the most part, we've assumed these fields are a modern phenomenon, generated by the dynamo action of moving plasma within stars and galaxies over billions of years. But what if some of this magnetism is not modern at all? What if it is primordial, a fossil relic left over from the universe's very first moments? This is not just a curious footnote. It's a radical idea that, if true, could completely reshape our understanding of the cosmic dawn and offer a compelling explanation for some of the most persistent anomalies we see in the microwave background. The implications of a primordial magnetic field are staggering. Imagine a universe so young that not even atoms had formed, a searing plasma of particles and energy. In that incredible cauldron, quantum fluctuations or phase transitions could have generated magnetic fields on a truly cosmic scale. These fields would then have been stretched and amplified by the inflationary expansion of the universe itself, weaving a faint, all-pervading magnetic tapestry into the very fabric of spacetime. This isn't just an abstract concept. Such a field would have actively participated in the drama of the early universe. It could have influenced how the primordial plasma sloshed around, subtly altering the formation of those first density fluctuations that eventually grew into galaxies. Most importantly for our story, it would have directly interacted with the light that became the cosmic microwave background, leaving behind a set of unique and potentially detectable fingerprints that we might have previously mistaken for noise or simply overlooked entirely. One of the most promising ways to find this ancient signature is through a beautiful physical effect known as Faraday rotation. This occurs when polarized light passes through a magnetized plasma. The magnetic field causes the direction of the light's polarization to slowly twist or rotate, like a needle on a compass being gently turned. The amount of rotation depends on the strength of the magnetic field and the density of the electrons it's passing through. This effect is a powerful tool for astronomers studying magnetic fields in galaxies today. But if a large-scale primordial field existed throughout the universe, it would have imprinted a specific, correlated pattern of Faraday rotation on the polarized light of the CMB itself. We wouldn't see this as a hot or cold spot, but as a distinct twist in the polarization angles across the sky, a subtle swirl that betrays the presence of an ancient, all-pervading force. Finding this pattern would be like discovering the universe's own magnetic fingerprint on its oldest photograph. This idea moves from fascinating to crucial when we consider some of the CMB's stubborn puzzles. Could a primordial magnetic field be the hidden actor behind the axis of evil or contribute to the oddities of the cold spot? A large-scale field would inherently break isotropy, introducing a preferred direction that could manifest as the strange alignments we observe. It could also create pressure effects that suppress or enhances structure formation in certain regions, perhaps explaining vast underdensities or other large-scale anomalies. Furthermore, the energy stored in such a field could contribute to the total energy budget of the early universe, potentially affecting the measured values of key cosmological parameters. In essence, a primordial magnetic field is a versatile theoretical tool that could plug several holes in our models at once. providing a unified explanation for phenomena that currently seem disconnected and bizarre. However, the hunt for this cosmic ghost is phenomenally difficult, a classic needle in a haystack problem where the haystack is the entire observable universe and the needle is almost impossibly faint. The primary challenge is the overwhelming contamination from modern magnetic fields. Our own galaxy is a brilliant source of polarized emission and Faraday rotation, its tangled magnetic field creating a complex foreground veil that completely obscures any primordial signal. Distant galaxies and clusters also generate their own fields, adding more layers of noise. Teasing apart a weak, uniform background signal from this brilliant and messy foreground is a task that demands more than just a powerful telescope. It requires a revolution in data analysis. Cosmologists must build incredibly sophisticated models of galactic magnetism, using observations across multiple wavelengths to predict and subtract its contribution with unprecedented accuracy. Any error in this modeling, any slight mischaracterization of how galactic dust polarizes light or how synchrotron radiation behaves, could either erase a real primordial signal or, worse, create a false one that sends researchers on a wild goose chase. Despite these immense challenges, many experts see this as one of the most exciting frontiers in cosmology. As astrophysicist Tina Koniashvili of Carnegie Mellon University has noted, the search for primordial magnetism is a golden window into an era of the universe we can never observe directly, a way to probe physics at energy scales far beyond any earthly particle collider. The absence of a detection so far is itself a profound result, placing tighter and tighter constraints on the maximum possible strength of any primordial field, and in doing so, ruling out entire classes of theoretical models for the universe's birth. The next generation of CMB experiments, like CMB S4 and the Simons Observatory, are being designed with this specific goal in mind. Their ultra-sensitive polarization measurements across many frequency bands will provide the cleanest data yet, offering our best ever chance to either finally detect this elusive fossil field or conclusively prove that the universe was born without one. This quest perfectly illustrates how modern cosmology is no longer a solitary pursuit. It is a deeply interdisciplinary effort, merging the cosmic scale insights of general relativity with the intricate plasma physics of magnetohydrodynamics, all in service of answering one of the most fundamental questions we can ask. Was magnetism there at the beginning, or is it solely a product of the cosmic structures that came after? Every great discovery in science is shaped not just by brilliant ideas, but by the tools available to test them. Our understanding of the cosmic microwave background is a story written by the evolving technology we've used to observe it, and each chapter is defined by what those instruments could, and crucially could not, see. The journey from the first tentative detection to today's ultra-high-definition maps is a tale of progressively wiping condensation from a cosmic window, each pass revealing a little more of the breathtaking view outside, while also making us acutely aware of how much fog still remains. Consider the very first map of the CMB produced by the COB satellite in the early 1990s. It was a monumental achievement, the first time humanity had ever seen the infant universe's face. But by today's standards, it was a blurry, impressionistic painting. COB resolution was remarkably coarse. Its vision was so fuzzy that it could only discern features in the sky larger than about 7 degrees across. To put that in perspective, that's about 14 times the width of the full moon. Imagine trying to read a message written on a distant billboard with a powerful telescope, but your lens is smeared with Vaseline. You can tell there are words there, and you might even make out some of the larger letters, but the fine print, the crucial details, the subtle nuances of the handwriting, all of that is completely lost to you. This fundamental limitation meant that COB confirmed the existence of the primordial ripples, but it could only see the very largest of them, an entire universe of smaller-scale fluctuations, along with any potential large-scale anomalies that didn't fit a smooth pattern, were simply invisible, hidden in a haze of low resolution. The universe appeared reassuringly simple and random because our tools were not yet sharp enough to discern any potential complexity. This began to change with the Wilkinson Microwave Anisotropy Probe, WMAP, which launched in 2001. Where COB gave us a blurry snapshot, WMAP provided a sharp photograph. Its resolution was over 30 times finer, allowing it to see details down to just a fraction of a degree. This was the moment the baby picture of the universe came into focus, revealing the intricate tapestry of hot and cold spots in stunning detail. It was with WMAP clearer vision that cosmologists first began to notice that something was slightly off. The large-scale fluctuations didn't look perfectly random. There seemed to be a strange asymmetry, a hint of a preferred direction, the first whispers of what would become known as the axis of evil. But was this a real feature of the universe or a flaw in the camera? WMAP, for all its power, had its own set of limitations. Its instruments were still susceptible to instrumental noise, and most importantly, it had a limited range of frequency bands. This made the arduous task of foreground subtraction, removing the contaminating glow of our own galaxy, incredibly difficult. Skeptics could reasonably argue that these strange large-scale patterns were not primordial at all, but merely artifacts of an imperfect cleaning process, faint smudges left behind after wiping away the galactic dust. The quest for ultimate clarity culminated in the European Space Agency's Planck satellite, the undisputed champion of CMB observation to date. Launched in 2009, Planck was a technological marvel designed to address the shortcomings of its predecessors. It didn't just have higher resolution, it had a wider sonic range for listening to the cosmos. Planck observed the sky in 9 different frequency bands, from 30 to over 950 gigahertz. This multi-frequency approach was its superpower. Think of it like a photographer who doesn't just have a better lens, but also a full set of specialized color filters. By viewing the sky in these different colors, Planck could isolate the true CMB signal from the foreground contaminants with a precision that was previously unimaginable. It was the first observatory that could truly separate the cosmic whisper from the galactic roar with high confidence. And what did this supreme clarity reveal? It confirmed the anomalies. The axis of evil was still there. The cold spot was still there, colder and more defined than ever. Planck's superior vision didn't erase the mysteries. It etched them deeper into the map, transforming them from curious maybes into stubborn realities that demanded an explanation. Yet for all its power, Planck was not all-seeing. Its limitations are the very reason cosmology did not end with its final data release. Every instrument has a fundamental noise floor, a point below which it cannot reliably detect a signal. For Planck, this noise, combined with the residual uncertainty in foreground modeling, especially from polarized galactic dust, meant it could only place upper limits on the most sought-after signal of all, the primordial B modes from inflation. It told us how quiet the universe is, but it couldn't definitively hear the faintest whisper we're listening for. Furthermore, every telescope has a beam size, the smallest patch of sky it can resolve. Planck's beam, though small, still blurred the very finest details on the largest scales, potentially smoothing over the sharp edges of any ultra-large-scale features. Its view of polarization, while revolutionary, was still like looking at a masterfully restored painting through a faint pane of glass. You can see the image clearly, but the most subtle textures and brushstrokes are softened. This brings us to the thrilling present and the near future. The legacy of Planck is not a finished map, but a detailed list of questions and a blueprint for the next generation of explorers. Projects like the Simons Observatory in Chile and the colossal CMB S4 project, which will deploy an army of telescopes across the Atacama Desert and the South Pole, are being built explicitly to see what Planck could not. Their goal is to improve sensitivity to polarization by an order of magnitude. They will have even more frequency channels to model foregrounds with ruthless precision, and they will use tens of thousands of superconducting detectors to drown out instrumental noise with a flood of pristine data. They are not just building a better camera, they are building a microscope for the cosmos, designed to detect the infinitesimally faint swirls of primordial gravitational waves and to scrutinize the large-scale anomalies with a clarity we can currently only dream of. They will be able to ask with real empirical force if the cold spot has a specific polarization pattern that betrays a cosmic texture, or if the large-scale asymmetry is accompanied by other telltale signs of new physics. The technological journey of CMB science is a powerful reminder that our view of the universe is never absolute. It is always filtered through the lens of our technology, and with each technological leap, we don't just get better answers, we learn to ask better, more profound questions. The mysteries we grapple with today may not be fundamental truths of nature, but merely reflections of our current technological horizon, waiting for the next great instrument to finally bring them into focus. Now, after this grand tour of cosmic anomalies and spectacular theories, we arrive at perhaps the most humbling and crucial question of all: how do we know any of this is real? When we stare at a map of the microwave sky and our eyes are drawn to a cold patch here or a strange alignment there, are we truly witnessing a crack in the foundations of physics, or are we simply falling for an illusion, a cosmic mirage born from our own brain's relentless desire to find patterns in the noise? This isn't just a philosophical musing, it's the bedrock of the entire scientific process, and it forces cosmologists to become masters of statistics, constantly wrestling with the specter of chance. The core of the problem lies in a fundamental cognitive bias we all share. The human brain is an exquisitely tuned pattern recognition machine. It's why we see faces in the clouds and animals in the constellations. This skill was essential for our survival, allowing our ancestors to spot a predator hiding in the dappled light of the forest. But this same talent becomes a liability when we're confronted with a vast, complex dataset like the cosmic microwave background. We will inevitably find shapes and correlations that feel significant, even if they are utterly random. To overcome this, scientists rely on a rigorous statistical framework designed to quantify the difference between a real signal and a lucky roll of the cosmic dice. They ask a specific question: what is the probability that this feature I'm looking at could have appeared in a universe that is perfectly described by our standard, vanilla-flavored Lambda CDM model? If that probability is extremely low, say less than 1 in 1,000, then we start to get excited. We say the feature is statistically significant, but here's where it gets fiendishly tricky. The CMB map is not a single, simple measurement. It's a universe of data points. When you have millions of pixels on a map, the chances of finding something that looks unusual in some place go up dramatically. This is known as the look elsewhere effect. To understand it, imagine flipping a coin 100 times. The odds of getting 10 heads in a row at some point during those flips are actually pretty good, even though the odds of getting 10 heads on 10 specific, pre-chosen flips are astronomically low. In cosmology, we're often guilty of flipping through the entire cosmic coin toss and then pointing to a run of 10 heads and declaring it a miracle, without accounting for the fact that we were searching through trillions of possible places for such a run to occur. This is why the initial confidence levels for anomalies often shrink when they are properly scrutinized. A feature that might appear to be a 1 in 10,000 fluke when considered in isolation might actually be a 1 in 50 occurrence once you account for the fact that you effectively checked 10,000 different places for such a fluke. This adjustment is not cheating. It's a necessary correction for the immense size of the dataset we're exploring. Compounding this issue is a related pitfall known as a posteriori statistics, or after-the-fact analysis. This is the practice of defining what constitutes an anomaly after you've already seen the data. It's the difference between saying, "I bet there's a particularly cold spot in the constellation Eridanus," and then looking to find it, versus making a full sky map, scanning it with your eyes, noticing a cold spot in Eridanus, and then calculating how unlikely it is. The first approach is a strong, testable prediction. The second is a recipe for self-deception because you've effectively tailored your definition of unusual to perfectly fit the data you already have. It's like drawing a bullseye around an arrow you've already shot into a barn door. Many of the anomalies we've discussed were found in exactly this way. They were surprises that jumped out of the data, not predictions that were later confirmed. This doesn't automatically make them wrong, but it does mean we have to apply an extra layer of skepticism and demand much stronger evidence before we accept them. So how do cosmologists combat these statistical demons? Their most powerful weapon is the universe itself, or more accurately, thousands of simulated ones. Using immense supercomputers, they run what are called Monte Carlo simulations. They create countless virtual universes, each one perfectly obeying the standard cosmological model with its random, Gaussian fluctuations. They then process these simulated skies through the exact same data pipelines and analysis software used for the real Planck or WMRP data, complete with simulated instrument noise and foreground contamination. This creates a vast library of what the universe is supposed to look like if the standard model is correct. Then they go hunting. They ask, in how many of these 10,000 fake universes do we see a cold spot as large and as cold as the one in Eridanus? In how many do we see a large-scale asymmetry as pronounced as the axis of evil? If, for example, such a feature appears in 5% of the simulations, then its statistical significance is said to be 95%, meaning there's a 1 in 20 chance it's just a fluke. This is the gold standard for testing anomalies. It's a way of quantifying the look elsewhere effect and our a posteriori biases all at once. The results of this rigorous process have been both sobering and fascinating. Many peculiar features that caused initial excitement have faded under this harsh statistical light. When you generate 10,000 random universes, you will inevitably create some that look very, very weird. You will get simulations with even larger cold spots, more dramatic alignments, and more striking voids than anything we see in our actual universe. As the statistician and cosmologist Andrew Jaffe has pointed out, the universe is under no obligation to be boring. The fact that we can create such bizarre-looking simulations from a perfectly standard model is a powerful reminder that chance alone can produce apparent miracles. This has led many in the field to urge extreme caution. They argue quite persuasively that the burden of proof lies with those claiming a discovery to demonstrate that their anomaly is not just a statistical ghost. And yet, the story doesn't end there. The most persistent anomalies, like the cold spot and the hemispheric asymmetry, have proven to be unusually stubborn. Even after the most rigorous statistical corrections, they linger at a confidence level of around 99%, a 1 in 100 chance of being a fluke. In daily life, those are fantastic odds, but in particle physics, the standard for a true discovery is 5 sigma, or a 1 in 3.5 million chance of being wrong. Cosmology often deals with unique, unrepeatable observations, so the standards are different, but the principle remains. 1 in 100 is intriguing, but it's not a slam dunk. It's the difference between a strong hint and a definitive discovery. This is why the debate continues. The anomalies are not yet strong enough to force a paradigm shift, but they are too persistent to simply ignore. They exist in a tantalizing limbo, a provocation that keeps scientists up at night, driving them to build better telescopes and develop more sophisticated statistical tools. This delicate dance between skepticism and open-mindedness is not a weakness of science. It is its greatest strength. It is the engine that drives us slowly, painstakingly, and honestly toward a deeper understanding of our truly bizarre cosmos. The persistence of these cosmic curiosities has not gone unanswered. While the standard Lambda CDM model remains the reigning champion for its incredible predictive power, its lingering puzzles have inspired a vibrant ecosystem of alternative cosmologies. These are not fringe ideas, but serious, mathematically rigorous theories proposed by respected physicists who are willing to ask a daring question. What if the foundation itself needs a tweak? These alternatives don't seek to overturn everything we know. Instead, they propose specific, targeted modifications to the standard model's ingredients, each one designed to potentially explain the anomalies that currently defy a comfortable explanation. One prominent avenue of exploration involves tinkering with the most famous force in the universe, gravity. Einstein's theory of general relativity has been spectacularly successful for a century, but its reign over the cosmic scale is not unchallenged. Theories of modified gravity, with names like MOND, modified Newtonian dynamics, and its relativistic extensions, propose that our understanding of gravity itself might be incomplete on the very largest scales. Instead of invoking vast amounts of invisible dark matter to explain the motions of galaxies, these theories suggest that the laws of gravity behave differently when the gravitational pull becomes incredibly faint. If true, this would have profound implications for the cosmic microwave background, the way galaxies clump together, and the precise pattern of the CMB's acoustic peaks are exquisitely sensitive to the amount and behavior of matter. A modified theory of gravity would predict a subtly different arrangement of those hot and cold spots, potentially erasing the need for dark matter and offering a new way to calculate the universe's expansion history that might resolve the Hubble tension. While these theories face their own significant challenges, particularly in explaining the precise observations of colliding galaxy clusters, they represent a bold attempt to solve several problems with a single, elegant shift in perspective. Then there are models that dare to reimagine time itself, proposing a cosmos without a definitive beginning or end. Leading this charge is the Nobel laureate Sir Roger Penrose with his conformal cyclic cosmology. This breathtakingly ambitious theory suggests that our universe is not the first and only one, but merely one episode in an endless cycle of eons. In Penrose's vision, the distant, heat-death future of our expanding universe, a cold, empty void where all matter has decayed and all black holes have evaporated, becomes mathematically indistinguishable from the hot, dense, featureless singularity of a new Big Bang. The end of one eon seamlessly becomes the beginning of the next in a conformal rebirth. This radical idea makes a very specific and testable prediction about the CMB. If our universe was born from the ashes of a previous one, then the collision of supermassive black holes from that prior eon would have sent out ripples of gravitational waves. When our universe inflated, those ripples would have been imprinted as faint, concentric circular patterns in the CMB's temperature map. Penrose and his colleagues have claimed to have found evidence of these Hawking points in the Planck data, though these claims remain highly controversial and have been heavily criticized by other cosmologists who argue the patterns are consistent with random noise. Regardless of its ultimate validity, conformal cyclic cosmology is a powerful example of how anomalies can inspire truly profound reimaginings of reality. Other theorists explore a simpler but equally radical notion that the cosmological principle itself is wrong. What if the universe is not homogeneous and isotropic on the largest scales? The idea of an inhomogeneous universe suggests that we might be living in a special place, not the center, but perhaps within a vast cosmic void that stretches for billions of light years. In this Hubble bubble scenario, the local underdensity of matter would affect our measurements of the expansion rate, potentially explaining the Hubble tension without any new physics. The light from distant supernova would be dimmer than expected, not because of accelerated expansion driven by dark energy, but simply because they are sitting in a denser part of the universe whose gravity is slowing the expansion relative to our emptier local region. Such a model would leave a clear signature on the CMB through the integrated Sachs-Wolf effect, creating specific large-scale patterns that could, in principle, be searched for. While current data suggests any such void would have to be improbably large to account for the observations, it remains a testament to scientists' willingness to question even the most foundational assumptions. It is crucial to understand that the vast majority of these alternative models currently lack the direct, corroborating evidence that supports the standard model. They often solve one problem while creating several new ones, yet their value is immense. They act as a necessary crucible for scientific creativity, forcing the mainstream to continually test and strengthen its own foundations. They provide a library of potential explanations, a toolkit of ideas that can be reached for if and when a definitive anomaly is confirmed. The history of science is not a straight line from ignorance to truth. It is a chaotic, vibrant process of proposal, critique, and refinement. The strange features in our cosmic microwave background are the sparks for that process, compelling the brightest minds to push at the boundaries of the possible and imagine a cosmos that is even stranger and more wonderful than we have yet dared to believe. Yet for all the profound questions raised by our current maps, the story of the cosmic microwave background is far from over. In many ways, it feels as if we are only just beginning to read the full text. The tantalizing anomalies and unresolved tensions we've uncovered are not dead ends. They are signposts pointing the way for a new generation of explorers armed with tools of such breathtaking sensitivity that they will make our current observatories look like child's toys. We are standing on the precipice of a new golden age of cosmology, defined by a global fleet of next-generation experiments designed to do one thing: listen more closely to the universe's first whisper than ever before. Leading this charge is an international armada of projects, each with a unique role to play in the coming decade. In the thin, frigid air of the Chilean Atacama Desert, the Simons Observatory is rapidly taking shape. This ambitious project is not a single telescope, but a coordinated array of instruments, including 3 small telescopes and 1 large one with a massive 6-meter aperture. Its location is strategically chosen. The high altitude and incredibly dry air minimize the atmospheric interference that plagues ground-based astronomy. But its true power lies in its detectors. The observatory will be equipped with over 60,000 superconducting detectors, each cooled to a fraction of a degree above absolute zero. This vast array will allow it to survey the sky with a speed and sensitivity that is an order of magnitude greater than anything that has come before, mapping the CMB's polarization in exquisite detail across a wide range of frequencies. This multi-frequency approach is its key to slaying the dragon of foreground contamination, allowing scientists to isolate the true cosmic signal from the polluting glow of galactic dust with a precision that was previously a distant dream. While the Simons Observatory will create the most detailed ground-based maps ever made, the ultimate clarity will come from above. Scheduled for launch later this decade, the Japanese-led LightBird satellite, which stands for the Light Satellite for the studies of B-mode polarization and inflation from dust, will embark on a mission of unparalleled scope. From its vantage point at the Lagrange Point 2, a stable gravitational spot in space 1,000,000 miles from Earth, LightBird will be completely free from the murky interference of our atmosphere. Its goal is singular and historic: to perform a full sky survey of the CMB polarization with the specific aim of detecting the primordial gravitational wave background, the holy grail of inflationary cosmology. LightBird designers are focusing on the largest angular scales on the sky, those most affected by the pesky gravitational distortions from intervening matter, precisely where the inflationary B-mode signal is predicted to be most prominent. By operating in space, LightBird can achieve a level of systematic error control that is simply impossible on the ground, offering our cleanest ever view of the vast cosmic canvas. And then there is the behemoth, the project that represents the culmination of decades of experience and technological progress, CMB S4, the Cosmic Microwave Background Stage 4. This is not merely a new observatory, it is a distributed infrastructure project on a colossal scale, envisioned as a network of telescopes deployed at both the South Pole and in the Atacama Desert. CMB S4 will be a collaboration involving hundreds of scientists from over 100 institutions. Its planned arsenal includes 21 telescopes outfitted with a staggering 500,000 detectors. This immense scaling up is necessary to achieve its primary science goal: to either detect the signature of primordial gravitational waves at a level far below the current limits, or to rule out a huge swath of inflationary models forever. The project's co-spokesperson, John Karlstrom of the University of Chicago, has framed it not just as a new telescope, but as a definitive experiment for inflation. He has said that CMB S4 will measure the CMB with such exquisite precision that it will effectively be limited only by the fundamental astrophysical foregrounds themselves, not by the technology. It is designed to be the last word, the instrument that will finally tell us if the simplest and most compelling versions of the inflationary paradigm are correct. The technological heart of all these endeavors is a quiet revolution in detector physics. The workhorse technology is the transition edge sensor, or TESS. These are not simple light meters. They are exquisitely sensitive thermometers made from a superconducting film held at the precise knife edge between its superconducting and normal states. A single photon from the CMB striking one of these sensors produces a tiny amount of heat, just enough to bump it out of superconductivity and cause a measurable change in its electrical resistance. By packing hundreds of thousands of these sensors into huge focal planes, these new experiments can capture an unprecedented flood of clean, high-fidelity data. Furthermore, advances in metamaterials, artificial materials engineered with properties not found in nature, are being used to create on-chip spectrometers and polarizers, allowing each detector to be precisely tuned to a specific frequency and polarization angle. This integrated approach minimizes noise and complexity, turning what was once a room-sized apparatus into a wafer-thin chip that can be mass-produced. It is this marriage of quantum materials science and large-scale engineering that enables the leap in sensitivity we are about to witness. The scientific promise of this coming data deluge is nothing short of transformative. For the first time, we will have the statistical power to move beyond simply noticing anomalies and begin to rigorously test their physical origins. Is the cold spot a statistical fluke, a supervoid, or the imprint of a cosmic texture? The deep, multi-frequency polarization maps from these observatories will provide a definitive answer. They will look for the specific polarization patterns that would be left behind by a collapsing texture or the shockwave of a bubble collision, signatures that are simply invisible in today's temperature maps alone. Similarly, the stubborn large-scale anomalies like the axis of evil will be subjected to a brutal new level of scrutiny. With the ability to model and subtract galactic foregrounds with near-perfect accuracy, scientists will be able to determine once and for all if these features are primordial scars on the universe or merely the ghostly afterimage of our own galaxy's magnetic field reflected in imperfect data processing. But perhaps the most profound hope lies in the potential for a complete surprise. The history of CMB science is littered with unexpected discoveries, from its initial detection to the revelation of its anisotropies. These new observatories are not just being built to answer the questions we already have. They are being built to reveal the questions we haven't even thought to ask. By mapping the sky with such incredible depth and precision, they could uncover entirely new phenomena, perhaps evidence for exotic particles from the early universe, signs of additional spatial dimensions, or clues about the nature of dark matter and dark energy that are completely orthogonal to anything we are currently investigating. As one project scientist for the Simons Observatory put it, we are building a microscope for the cosmos. We have a list of things we expect to see, but I am most excited for the thing on that map that makes us all say, "What is that?" This forward-looking sentiment captures the true spirit of this new era, a blend of confident expectation and humble anticipation, a recognition that the universe has always been far stranger and more wonderful than our theories could predict, and that the best undoubtedly yet to come. Yet the quest to decode the cosmic microwave background is not a solitary endeavor undertaken by astronomers alone. It represents one of the greatest collaborative efforts in the history of science, a grand synthesis where the boundaries between disciplines blur to reveal a deeper, unified picture of reality. The signals hidden within this ancient light are so subtle, and their implications so profound that interpreting them requires a convergence of expertise from fields that, on the surface, seem to have little in common. The most precise map of the universe is, in many ways, a mirror reflecting the combined intellect of particle physicists, string theorists, data scientists, and engineers, all bringing their unique tools to bear on a single, monumental puzzle. Consider the intimate dialogue between cosmology and particle physics. The very first moments of the universe were a realm of unimaginably high energies, a domain that particle physicists strive to recreate in massive underground colliders like the Large Hadron Collider at CERN. While these machines can only briefly simulate a fraction of the energy present at the birth of the cosmos, the particles and forces they discover provide the essential ingredients for our models of the early universe. The discovery of the Higgs boson, for instance, wasn't just a triumph for particle physics. It was a crucial piece of the cosmological puzzle. The Higgs field is a scalar field, and its properties provide a tangible, proven example of the kind of field that theorists propose drove the inflationary expansion. Understanding how the Higgs behaves gives cosmologists vital clues about how the hypothetical inflaton field might have operated, shaping the predictions for what patterns we should, or shouldn't, see imprinted in the CMB. It's a beautiful feedback loop. Particle accelerators test the physics of the very small to explain the universe at its very largest, while the CMB provides a unique experimental testbed that can either validate or rule out their grand unified theories. A cosmologist analyzing the statistical properties of the microwave background is, in effect, conducting an experiment on particle physics at energy scales 1 trillion times beyond the reach of any earthly machine. This collaboration extends even further into the abstract realm of string theory. For decades, string theory has been criticized for its lack of testable predictions, often seen as a beautiful but untouchable mathematical construct. The study of the CMB is beginning to change that. String theory naturally predicts a vast landscape of possible universes, each with different physical constants and laws, a theoretical underpinning for the multiverse concept. Some versions of the theory also predict the existence of specific exotic objects, like cosmic strings or textures, which would leave unmistakable imprints on the CMB. While definitive evidence remains elusive, the search for these signatures provides a crucial bridge between abstract theory and observable reality. String theorists are now working directly with data analysts, translating their complex mathematical predictions into specific, measurable statistical signatures that can be hunted for in the Planck data. This partnership forces a level of concrete specificity onto the theory, moving it from pure mathematical speculation into the domain of empirical science. A subtle, unexplained correlation in the CMB's polarization map could one day be the key that unlocks the hidden dimensions of string theory. Perhaps the most underappreciated partner in this endeavor is computational science. The raw data from an instrument like the Planck satellite is not a ready-made picture of the infant universe. It is a colossal, noisy, and contaminated dataset that requires Herculean effort to clean and interpret. The task of separating the pristine CMB signal from the foreground glow of our galaxy is a computational nightmare of epic proportions, a problem that demands innovative algorithms and staggering processing power. This is where experts in machine learning and statistics have become indispensable. They develop sophisticated techniques like Bayesian inference and blind component separation, which allow computers to essentially teach themselves to recognize and isolate the different sources of microwave emission across the sky. Furthermore, the interpretation of the clean data relies entirely on Monte Carlo simulations. Cosmologists use the world's most powerful supercomputers to run millions of simulations of the universe, each with slightly different physical parameters, to see which one produces a virtual CMB that most closely matches the one we observe. This entire process, from data cleaning to parameter estimation, is a monumental feat of data science. Without the relentless advance of computing power and the creative genius of algorithm developers, the exquisite maps from Planck would be nothing more than meaningless static. The cosmic microwave background has, in effect, given rise to a new field of astroinformatics, where the ability to write elegant code is just as important as the ability to write elegant equations. This cross-pollination of ideas is where the most exciting breakthroughs are often born. A perfect example is the development of the algorithms used to search for the specific swirling patterns of primordial B-mode polarization. The techniques needed to detect this incredibly faint signal were not invented by astronomers. They were adapted from the field of computer vision, where similar algorithms are used to enhance fuzzy photographs or detect subtle patterns in medical imagery like mammograms. The challenge of finding a weak, correlated signal buried in overwhelming noise is a universal problem, and the solutions developed in one field can often provide the key to unlocking another. These collaborations are not without their challenges. Scientists from different domains speak different technical languages, use different mathematical tools, and often have vastly different cultural approaches to problem solving. A particle physicist might be focused on elegant mathematical beauty, while a data scientist is concerned with computational efficiency and error bars. Bridging these gaps requires patience, humility, and a shared commitment to the larger goal. The success of missions like Planck is a testament to this, as they are not run by a single institute, but by vast international consortia comprising hundreds of scientists from dozens of countries, each contributing a specialized piece of the puzzle. This is modern big science at its best, a deeply human enterprise that recognizes that the universe's deepest secrets are too complex for any one mind or any one field to unravel alone. The clues we missed in the microwave are not just hidden in the data, they are waiting at the intersections between our artificial intellectual boundaries, ready to be discovered by those willing to collaborate. It's easy to look at these colossal scientific endeavors with their 500,000 detectors and their multi-billion-dollar price tags and see them as abstract pursuits, the exclusive domain of PhDs in ivory towers. But that perspective misses the most beautiful truth of all. This quest to understand the cosmic microwave background is at its heart a profoundly human one. It's driven by the same innate curiosity that makes a child stare up at a starry sky and ask, where did all of this come from? This isn't just science for scientists. It's a story about our origins, a shared inheritance that belongs to every single one of us. The light from the dawn of time is falling on all of us right now, and the effort to understand its message enriches our culture, fuels our technology, and fundamentally deepens our connection to the cosmos we call home. One of the most powerful ways this knowledge touches our lives is through the incredible technological spin-offs it generates. The relentless drive to build a more sensitive radio receiver or a more stable cryogenic cooler for a CMB telescope doesn't just benefit astronomy, it ripples outwards, catalyzing innovation across countless industries. The need to process the unimaginably complex data from the Planck satellite pushed the boundaries of computing and algorithm development, leading to advances in machine learning and data compression that now power everything from medical imaging to financial modeling. The exotic superconducting materials perfected for those transition-edge sensors are finding applications in new forms of medical diagnostics and quantum computing. Even the sophisticated software used to clean foreground contamination from cosmic maps is being adapted to improve the clarity of satellite imagery for environmental monitoring and disaster response. Dr. John Kovac, a leader in the BICEP project, often emphasizes this point in public talks, noting that we are not just mapping the sky, we are building the tools for tomorrow's economy. The pursuit of pure, fundamental knowledge, free from the immediate pressure of commercial application, has a proven track record of accidentally inventing the future. The internet, the GPS in your phone, and countless medical breakthroughs all sprang from similar seeds of curiosity-driven research. The next generation of CMB telescopes, with their armies of ultra-sensitive detectors, is essentially a massive engineering project to push material science, optics, and computing to their absolute limits, and we cannot yet imagine what practical wonders that effort will eventually unlock. Beyond the tangible technological benefits, the story of the CMB plays a vital role in shaping our culture and educating the next generation. This is where the work moves from the laboratory into the hands of talented educators and artists who translate these complex ideas into experiences that ignite a sense of wonder. Planetariums around the world have made the Planck all-sky map a centerpiece of their shows, allowing visitors to be literally surrounded by the universe's first light, to see the hot and cold spots that became their galaxies projected onto a vast dome above them. This isn't just a pretty picture, it's a visceral, awe-inspiring experience that makes an abstract concept feel immediate and real. Museums have created stunning interactive exhibits where you can create your own universe, tweaking the amounts of dark matter and dark energy to see how it changes the pattern of the CMB and ultimately the fate of everything within it. These are more than just displays, they are gateways to scientific literacy, teaching the public not just facts, but the scientific process itself, how we question, test, and refine our understanding of the world. This outreach extends even further through the growing world of citizen science. Projects like Project Name invite anyone with an internet connection to help cosmologists analyze real CMB data, sifting through it to identify unusual features or help classify foreground galaxies. This democratization of discovery is powerful. It breaks down the barrier between the scientist and the public, creating a collaborative community of learners. An educator at the American Museum of Natural History, when asked about the value of this, put it perfectly. We're not just teaching people about the Big Bang, we're inviting them to participate in the great human adventure of discovery. When someone contributes, even in a small way, to something as grand as mapping the infant universe, it changes their relationship with science. It becomes their story too. This fosters a sense of shared ownership and wonder, combating misinformation and building a society that values evidence, critical thinking, and the humble yet relentless pursuit of truth. Ultimately, the study of this ancient light does something even more fundamental. It provides a profound sense of perspective. In a world often consumed by short-term conflicts and divisions, the CMB offers a timeless vantage point. It reminds us that we are all, without exception, made of stardust forged in the hearts of ancient suns, and that we all live on a fragile, pale blue dot suspended in a vast and breathtakingly beautiful cosmos. This knowledge doesn't provide easy answers to our earthly problems, but it can inspire a deeper sense of unity and responsibility. It's a humbling and simultaneously empowering realization that we are the universe become conscious, able to look back at its own beginnings and ask questions about its own nature. This pursuit of knowledge for its own sake, this desire to understand our place in the grand scheme of things, is one of the most noble and defining qualities of our species. By sharing the mysteries of the microwave background, scientists and educators aren't just passing along information, they are keeping that flame of curiosity alive, ensuring that the next generation will continue to look up, to question, and to wonder, adding their own chapter to the greatest story ever told. But as we marvel at the technological triumphs and the profound insights gleaned from these cosmic observations, we must also pause to ask a more grounded, deeply human question. What is the true cost of this knowledge? The pursuit of understanding the cosmic microwave background is not merely an intellectual exercise. It is a monumental undertaking that consumes vast resources, involves complex international politics, and carries a tangible environmental footprint. It forces us to confront the ethical dimensions of big science, where the hunger to answer the universe's biggest questions must be balanced against the immediate needs of our world. A project like the Planck satellite had a price tag stretching into the hundreds of millions of euros. The upcoming CMB S4 project is expected to cost well over $500 million. These are staggering sums, and it is not only valid but essential to ask whether this is the best use of our collective wealth, especially when that same money could fund countless other urgent priorities, from combating poverty and disease to addressing the climate crisis or improving education. This is not a question with an easy answer, but a necessary tension that the scientific community and society at large must grapple with openly and honestly. The justification for such immense investment often hinges on two powerful arguments: serendipitous technological innovation and the immeasurable value of inspiration. History is littered with examples of pure research yielding unexpected, world-changing practical applications. The very World Wide Web you might be using to watch this video was invented at CERN to help particle physicists share their data. The exquisite sensors developed to read the faint whisper of the CMB are pushing the boundaries of material science and cryogenics, with potential future uses in medical imaging, quantum computing, and global communication networks. This technological spin-off effect is a powerful engine of progress, but it is inherently unpredictable. We cannot know which specific invention will spring from which experiment. We only know that a consistent investment in fundamental, curiosity-driven research has a proven track record of creating the tools that shape our future economy and improve our daily lives. Perhaps even more profound is the inspirational dividend. A single image from the James Webb Space Telescope or a map from Planck can captivate millions, igniting a passion for science and engineering in a generation of young minds. This is not a trivial outcome. The complex challenges of the coming century will require a scientifically literate populace and a steady pipeline of brilliant, creative problem solvers. By funding missions that capture the public's imagination, we are not just buying data, we are investing in the intellectual capital of our future. However, this global endeavor also raises critical questions about equity and collaboration. Large-scale CMB projects are almost exclusively led by a consortium of wealthy nations and elite institutions. While there are efforts to include developing countries, the playing field is far from level. This creates a risk of a new form of scientific colonialism, where the global south provides raw data or telescope sites without reaping the full benefits of intellectual ownership, technological training, and the economic advantages that come with high-tech research and development. Addressing this requires a conscious and proactive commitment to true partnership funding educational exchanges, building local technical capacity in host countries, and ensuring that the fruits of discovery, from patents to publications, are shared as widely as possible. The cosmos belongs to everyone. The means to understand it should not be hoarded by a privileged few. Furthermore, the very act of building these monuments to science has an environmental cost that can no longer be ignored. Launching a single satellite requires immense amounts of fuel, contributing to atmospheric pollution. The construction of massive observatories in remote, pristine environments like the Atacama Desert or the Antarctic Plateau, while necessary for clear skies, disturbs fragile ecosystems. The scientific community is increasingly aware of this footprint and is taking steps to mitigate it, from designing more energy-efficient supercomputers to powering remote stations with renewable energy and conducting thorough environmental impact assessments before breaking ground on new facilities. The goal is to ensure that in our quest to understand the universe, we do not irreparably harm our own planet in the process. Ultimately, the decision to fund such grand projects is a reflection of our societal values. It is a statement that alongside our urgent practical needs, we also value beauty, curiosity, and the profound human desire to know our place in the cosmos. It is a bet on the long term, a belief that the seeds of knowledge we plant today may grow into a forest of understanding and capability that will shelter future generations in ways we cannot yet imagine. This does not absolve us of the responsibility to debate the costs and to ensure that the pursuit of cosmic truth is conducted as ethically and sustainably as possible. But it reminds us that humanity has always been driven by two equally powerful forces: the need to fix what is broken at our feet and the irresistible urge to look up at the stars and ask why we are here. Balancing these impulses is one of the great challenges of our time, a delicate equation where the value of a single clue hidden in the ancient microwave static must be weighed against the very real and pressing needs of the world that is listening for it. Yet perhaps the most humbling philosophical implication lies not in the answers the CMB provides, but in the profound questions it forces us to confront about the very nature of knowledge and observation. Our entire view of the cosmos is filtered through a fundamental limitation called the cosmic horizon. Because the universe has a finite age and light has a finite speed, we can only observe a spherical volume of space about 93 billion light-years across. Everything beyond that is forever hidden from us. No signal, no information, no light from those regions has had time to reach us since the Big Bang. The cosmic microwave background is the ultimate wall, the final screen. It is the oldest light we can possibly see, but it is not the edge of the universe. It is merely the edge of our observable universe. This leads to a dizzying possibility championed by physicists like Max Tegmark, that the total, true universe could be mind-bogglingly larger than the patch we inhabit, perhaps even infinite. If that's the case, then every possible configuration of matter must, by the laws of probability, repeat itself an infinite number of times. Somewhere beyond that horizon, there could be an identical version of you watching an identical version of this video, living a life indistinguishable from your own. This isn't necessarily science fiction. It's a direct mathematical consequence of an infinite universe governed by the same physical laws everywhere. The CMB, by defining the limits of our vision, simultaneously forces us to grapple with the terrifying and exhilarating possibility of the infinite. This directly challenges centuries of philosophical thought about our special place in the cosmos. The Copernican principle, which dethroned Earth from the center of the universe, is now extended to its logical extreme. Not only are we not at the center of space, but our entire observable universe, with its hundreds of billions of galaxies, might be an utterly typical, unremarkable region within a far vaster and more exotic whole. The anomalies we see, like the axis of evil or the cold spot, might not be universal laws at all. They might simply be local geography, the particular arrangement of our cosmic neighborhood, with no more fundamental significance than the particular mountain range you happen to be born near. This radically shifts the goal of cosmology. As the philosopher of science Sean Carroll argues, we might have to abandon the dream of finding a single, unique theory of everything that predicts exactly why our universe looks precisely this way. Instead, the goal becomes finding a theory that allows for a vast landscape of possibilities, a multiverse of which our universe is just one rather generic example. The CMB data, with its strange and potentially unrepresentative features, becomes the key piece of evidence pushing us toward this profoundly humbling and expansive view of reality. This journey from raw data to deep philosophy showcases a beautiful synthesis of human inquiry. The physicist and the philosopher are engaged in the same essential project, using different tools to probe the same fundamental mysteries. The cosmologist provides the precise, empirical map, the detailed spectrum of temperature fluctuations, the polarization patterns, the statistical significance of an anomaly. The philosopher then steps in to ask what it all means. What does this tell us about the nature of time, given that we are looking into the past? What does it say about causality and the initial conditions of existence? How does the act of observation itself shape the reality we perceive? The CMB is the ultimate bridge between these two worlds. It is a dataset that can be analyzed with complex mathematics, but it is also a profound symbol. The afterglow of creation, the oldest story ever told, written in the faintest whisper of radiation. It reminds us that every scientific measurement is ultimately a philosophical statement, a step in our eternal quest to understand not just how the universe works, but what it is and what our place within it truly means. If the previous generation of satellites gave us high-definition images of the infant universe, then the European Space Agency's Planck mission delivered nothing less than an ultra-high-resolution, scientifically calibrated masterpiece. Launched in May 2009 atop an Ariane 5 rocket, Planck was not merely an upgrade, it was a philosophical shift in our approach to mapping the cosmos. Its primary objective was audacious in its simplicity, to measure the remnants of the Big Bang with such exquisite precision that it would either definitively confirm our standard model of cosmology or break it beyond repair. For over 4.5 years from its vantage point at the second Lagrange point, a stable gravitational spot in space 1,000,000 miles from Earth, this technological marvel performed its silent ballet, scanning the entire sky not once but multiple times. Its instruments, cooled to just a fraction of a degree above absolute zero, were so sensitive they could detect variations in the cosmic microwave background's temperature of a few millionths of a degree. This wasn't just looking at the universe's first light, it was listening to its faintest whisper with a clarity never before imagined. The legacy of this monumental effort is a dataset that fundamentally defines modern cosmology. Planck's most celebrated achievement was its breathtakingly precise measurement of the key ingredients of our universe. It told us, with an uncertainty of less than 1%, that our cosmos is composed of about 4.9% ordinary matter, the atoms that make up stars, planets, and us. It pinned down the amount of cold, dark matter, the invisible scaffolding of the cosmos, to 26.8%. And it precisely quantified the mysterious dark energy driving the accelerated expansion of the universe at 68.3%. These numbers are the bedrock upon which all of 21st century cosmology is built, but perhaps even more profound was its confirmation of the Standard Model's specific predictions for the cosmic primordial fluctuations. The mission's map of the CMB's temperature anisotropies was a near-perfect match to the predictions of the Lambda CDM model, a resounding triumph that earned it the nickname, the model's best friend. It seemed to present a universe that was, at its birth, almost impossibly well-behaved and predictable. Yet, hidden within this stunningly precise data was a collection of ghosts, persistent, nagging anomalies that refused to be smoothed away by better measurements. Planck's superior vision did not resolve the mysteries first hinted at by WMRP. It etched them deeper into the map with indelible ink. The mission confirmed, with greater confidence than ever before, the existence of the so-called axis of evil. This perplexing large-scale asymmetry, where one hemisphere of the sky shows stronger temperature fluctuations than the other, was not an artifact of a lesser instrument. It was a feature of the universe itself, staring back at scientists from the most precise data ever collected. Similarly, the enigmatic cold spot in the constellation Eridanus was not only confirmed but was found to be even colder and more statistically significant than previously thought. Planck's data also reinforced other curiosities, like the curious lack of correlation in the temperature fluctuations at the very largest angles and an unusual alignment of the largest scale features. These weren't minor quirks, they were fundamental cracks in the otherwise smooth facade of the Standard Model, and Planck's unparalleled precision made them impossible to dismiss as mere measurement error. Simultaneously, while these anomalies were being reinforced, Planck was also acting as a ruthless gatekeeper, slamming the door on a host of alternative theories and exotic ideas. This is the mission's fascinating dual legacy. It both heightened mystery and enforced discipline. For instance, the search for primordial non-gaussianity deviations from perfect randomness that would point to more complex physics during inflation came up almost entirely empty. Planck's data placed incredibly tight constraints on these effects, effectively ruling out a wide range of elaborate multi-field inflation models and compelling theorists to return to the drawing board. Its search for evidence of cosmic strings, the hypothetical, ultra-dense cracks in spacetime, also yielded no definitive detection. placing strict upper limits on their possible influence. And in the high-stakes hunt for primordial B-mode polarization, the smoking gun for cosmic inflation, Planck's results were definitive. It saw no convincing evidence. While it did map the polarization of the CMB for the first time across the entire sky, the primordial gravitational wave signal remained hidden beneath other sources of noise, allowing Planck to do little more than set a new, stricter upper limit on how powerful inflation could have been. In each of these cases, Planck didn't just fail to find something, it actively constrained the realm of what is possible, narrowing the boundless landscape of theoretical speculation into a more manageable, evidence-based field of play. However, this incredible precision came with its own set of profound limitations, many of which are inherent to the Herculean task of observing the universe itself. The most significant of these is the ever-present challenge of foreground contamination. Despite its 9 frequency channels, which allowed for the most sophisticated foreground subtraction ever attempted, the process remained fraught with uncertainty. The mission's final maps are the result of incredibly complex algorithms that model and then subtract the emission from our own galaxy's dust and synchrotron radiation. The entire endeavor rests on the accuracy of our astrophysical understanding of these foregrounds. If our models of how interstellar dust polarizes light are even slightly incorrect, the subtraction process could either leave behind residual artifacts that mimic primordial anomalies or, perhaps more worryingly, scrub away a genuine, faint signal from the early universe. This uncertainty is the single greatest source of ongoing debate about Planck's most puzzling findings. Skeptics can still argue, with some justification, that features like the large-scale asymmetry could be the lingering ghost of an imperfectly removed galactic foreground, a final smudge on the lens that we mistake for a feature of the distant cosmos. This inherent limitation means that Planck's ultimate gift to science may not be a set of final answers, but a perfectly defined set of new and better questions. The mission represents a pinnacle of a certain kind of observational science, pushing technology to its absolute limit to extract every last photon of information from the cosmic microwave background. It took us to the precipice of what is possible from measuring temperature and large-angle polarization alone. Its legacy is a paradox. It simultaneously delivered the most convincing proof of our standard cosmological model, while also providing the most robust evidence that the model is incomplete. It showed us a universe that is almost perfectly described by 6 simple parameters, yet one that also displays faint, persistent whispers of something else, something beyond the current paradigm. Planck's story is the ultimate case study in the iterative, self-correcting nature of science. It didn't complete the picture of the cosmos. It completed a specific chapter, providing the definitive data that allows us to close the book on certain questions and confidently, if humbly, open a new one. It handed the baton to a new generation of experiments, like the Simons Observatory and Light Bird, whose specific design is a direct response to the paths Planck carved out and the walls it encountered. The mission's true triumph lies in knowing not just what we know, but in so perfectly defining what we have yet to learn. Faced with the tantalizing whispers of anomalies in the cosmic microwave background, cosmologists are confronted with a fundamental dilemma. Is the cold spot a genuine cosmic wound, or is it simply a statistical fluke that our pattern-seeking brains have latched onto? Does the axis of evil point to a profound violation of a core cosmological principle, or is it an illusion created by our imperfect view of the sky? To answer these questions, we cannot simply look harder at the same data. Instead, we must build entire universes from scratch, running the tape of cosmic history over and over again to see how often such strange features appear by pure chance. This is not a metaphor, it is the daily work of modern cosmology, conducted not with telescopes, but with some of the most powerful supercomputers on the planet. This incredible process begins with a set of initial conditions and a recipe, a specific theoretical model for how the universe should behave. A cosmologist might start with the standard Lambda CDM model, programming in the precisely measured amounts of dark matter, dark energy, and the spectrum of primordial fluctuations as predicted by a simple inflationary theory. With these ingredients set, they press the virtual start button. The simulation then runs the laws of physics forward in time, solving the immensely complex equations of general relativity and fluid dynamics on a cosmic scale. It models the gravitational collapse of dark matter halos, the formation of the first stars and galaxies, and the propagation of light through the expanding cosmos. The final, crucial step is to generate a synthetic, or a mock, cosmic microwave background map from this virtual universe. This involves calculating how the primordial photons would have interacted with the matter distribution right at the moment of recombination, and then tracing their path all the way to a hypothetical virtual observer. The result is a perfect, pristine CMB map, exactly what we would see if that particular theoretical model were an absolutely perfect description of reality. But the true power of this technique lies in its repetition. Scientists don't just run one simulation, they run thousands, even millions of them. This massive ensemble of virtual universes, known as a Monte Carlo simulation, creates a comprehensive library of what the cosmos is supposed to look like under the assumptions of the standard model. It effectively defines the bell curve of cosmic normality. With this vast dataset in hand, researchers can then perform a profound and humbling test. They take a puzzling feature from our real universe, like the size and coldness of the cold spot, and they go searching through their library of mock universes. They ask a simple quantitative question: in how many of these 10,000 perfectly standard simulations does a feature at least as large and as cold as the one we see appear just by random chance? The answers provided by these digital laboratories have been both sobering and illuminating. In the case of the cold spot, early simulations suggested that such a pronounced feature was exceedingly rare, appearing in far less than 1% of cases. This was the initial evidence that sparked excitement and speculation about exotic causes like cosmic textures or multiverse collisions. However, as the simulations have grown more sophisticated, incorporating more detailed physics and better statistics, the story has become more nuanced. More recent analyses suggest that while a spot that cold is indeed unusual, the probability of finding some kind of unusually large cold patch somewhere on the map is actually much higher, perhaps on the order of 1 or 2%, when you account for the fact that we are scanning the entire sky for anomalies. This doesn't completely solve the mystery, but it tempers the initial excitement, reminding us that the universe is under no obligation to look perfectly uniform, and that even a perfectly random distribution will, by its very nature, contain a few eyebrow-raising outliers. The same rigorous process has been applied to the axis of evil and the large-scale hemispheric asymmetry. Simulations have shown that finding a preferred direction of that apparent strength in a purely random, isotropic universe is also a relatively low probability event, but not an impossible one. The key insight from these virtual experiments is that our real universe sits in a somewhat uncomfortable middle ground. These anomalies are just a little too pronounced to be easily dismissed as flukes, yet not so overwhelmingly obvious that they force us to immediately discard our entire standard model. They exist in a tantalizing zone of persistent intrigue, a statistical purgatory that drives the need for ever more precise observations and ever more realistic simulations. Beyond just testing for flukes, these supercomputer universes serve as a crucial testing ground for alternative theories. A theorist who proposes a new model of inflation involving multiple fields, or a modification to gravity, or the existence of primordial magnetic fields, can now plug those equations into a simulation. They can run their alternative model forward to generate its own unique set of mock CMB maps. The ultimate test is then to compare this new, exotic virtual sky to the actual, observed Planck data. Does the new model produce a cold spot more frequently? Does it naturally generate a large-scale asymmetry without breaking other well-established predictions? Does it leave a specific, detectable fingerprint in the polarization patterns that we could go looking for with the next generation of telescopes? This process transforms wild, speculative ideas into concrete, testable hypotheses. It allows the data to act as a ruthless arbiter, killing off entire families of theories that fail to reproduce the world we see, while providing a lifeline to those that show even a hint of promise. The entire endeavor is utterly dependent on a silent revolution in computational power. The first CMB simulations were crude, low-resolution affairs that could only capture the broadest features. Today's state-of-the-art simulations with names like Achu and Flamingo are computational marvels. They track trillions of particles across volumes of space billions of light-years wide, resolving the formation of individual galaxies while simultaneously capturing the universe's grandest patterns. This requires petabyte-scale data storage and months of runtime on the world's fastest supercomputers. The algorithms themselves have become incredibly sophisticated, capable of modeling not just gravity and hydrodynamics, but also magnetic fields, cosmic rays, and the feedback from supermassive black holes and supernova. This relentless advance in computing is what has turned cosmology from a science of pure observation into a true experimental science, albeit one where the experiments are conducted in silicon rather than in a lab. It provides the essential context that turns a curious feature in a map into a quantifiable clue, guiding us steadily, if slowly, toward a deeper and more complete understanding of the cosmic dawn and the strange messages it has left for us in the microwave static. It's a fascinating truth that the deepest scientific discoveries rarely remain confined to the pages of academic journals. They seep into the very fabric of our culture, becoming part of our shared mythology and a new language for expressing our oldest questions. The cosmic microwave background, this most abstract and data-rich of concepts, has done exactly that. It has transcended its origins in astrophysics to become a powerful symbol and a potent source of inspiration in art, music, and literature, transforming from a graph on a screen into a modern-day cultural touchstone for wonder. This journey from the Planck satellite to the art gallery is a beautiful reminder that the impulse to understand the universe and the impulse to create are two sides of the same human coin, both driven by a profound need to find meaning and beauty in the cosmos. One of the most direct and visceral ways the CMB has entered our visual culture is through its own inherent, if hidden, beauty. The raw data from missions like WMAP and Planck is a grid of numbers, a spreadsheet of temperature variations. But when that data is translated into a visual map with cooler areas rendered in deep blue and warmer areas in fiery red, it creates an image of startling and ethereal beauty. This full sky map, often depicted as an oval, has become an icon. It looks like a cosmic eye, a radiant mandala, or an abstract expressionist painting writ across the heavens. Artists and data visualizers have seized upon this, creating stunning high-resolution prints and interactive installations where viewers can literally lose themselves in the details of the infant universe. These visualizations do more than just look pretty. They perform a crucial act of translation. They make the incredibly abstract concept of quantum fluctuations stretched across space instantly graspable. You don't need to understand the physics to feel the emotional weight of looking at the universe's first photograph. This image has graced the covers of magazines, been projected onto the domes of planetariums, and featured in countless documentaries, becoming the definitive visual shorthand for the Big Bang itself. It's a rare instance where the unaltered data of science is itself a work of profound art. This synergy between data and artistry has sparked a whole movement of artists who use cosmology not just as a subject, but as a medium. The composer and multimedia artist John Boswell, under the name Melody Sheep, is a prime example. His celebrated Symphony of Science series and his film, Time-Lapse of the Entire Universe, use the Planck CMB map as a central visual motif. He pairs these visuals with a soaring musical score, often sampling the awestruck voices of scientists like Carl Sagan. In his work, the cold spot isn't a statistical anomaly, it's a dramatic, mysterious crater on a cosmic landscape. The overall map becomes a character in a narrative about our origins, its texture and pattern providing a visual rhythm that complements the music and the words. Boswell's approach demonstrates how artistic interpretation can amplify the emotional resonance of scientific discovery, making the feeling of cosmic wonder accessible to millions who might never read a scientific paper. Beyond the digital realm, the CMB has also influenced more traditional fine art. The painter and sculptor Josiah McElhenney creates breathtakingly beautiful glass sculptures that are direct responses to cosmological ideas. One of his most famous works, The End of the Dark Ages, is a complex chandelier-like structure whose form and etched patterns are inspired by discussions with cosmologists about the large-scale structure of the universe and the patterns imprinted by the Big Bang. While not a literal map, his work captures the essence of the concept, the idea of a latent structure, a frozen moment of initial order from which all complexity emerges. He has spoken about wanting to create a visual metaphor for the moment when the universe became transparent to light, a direct nod to the epoch of recombination that gave us the CMB. His art doesn't explain the science, it feels like the science. It uses the emotional language of beauty, light, and reflection to evoke the same sense of grandeur that a cosmologist might feel when studying the Planck data. The influence extends powerfully into the literary world as well. Poets have found a rich vein of metaphor in the ancient light. The CMB becomes the fossilized glow of creation, the echo that outlives the shout, or a palimpsest on which the story of everything is written. In science fiction, its implications are explored narrative. Authors like Alastair Reynolds use the anomalies in the CMB as pivotal plot devices, imagining them as evidence of cosmic engineering by unimaginably advanced civilizations, or as scars from a war between universes. In these stories, the cold spot might be a void deliberately carved out by a godlike intelligence, or the axis of evil might be the gravitational shadow of a parallel reality. This speculative leap is more than just entertainment. It's a form of philosophical play. It uses the established facts of science as a springboard to explore the deepest questions about our place in the cosmos, the nature of reality, and the possibility of other intelligences. It shows that the CMB is not a closed book but an open invitation to imagine. This cultural permeation matters because it democratizes wonder. Not everyone can access the complex mathematics behind the Lambda CDM model, but everyone can be moved by a piece of music inspired by it or stand in awe before a visualization of the universe's first light. When an artist like composer Dan Romer incorporates manipulated sonifications of Planck data into a film score, He is translating cosmic history into an emotional experience. When a documentary filmmaker lays a narration about the search for meaning over a slow zoom into the Planck map, they are connecting the scientific quest to a universal human yearning. The artist Leah Halloran, whose work explores the intersection of art and science, has described this process as a form of dialogue. She says that science gives her a visual vocabulary for the sublime, a way to grapple with concepts too vast for words alone. In return, her art gives those concepts a tangible form, allowing others to feel their significance in an immediate, visceral way. This cultural feedback loop enriches everyone. It gives scientists a reminder that their work stirs the human soul, and it gives the public a gateway into the awe-inspiring realities of the universe we inhabit. The cosmic microwave background, in the end, is more than just radiation. It is a mirror. In its subtle patterns, scientists see the blueprint of the cosmos, and artists see a reflection of our endless, beautiful struggle to understand it. If this journey through the secrets of the microwave background has sparked a deeper curiosity, the beautiful news is that you don't need a doctorate or a radio telescope to continue the exploration yourself. The world of cosmology is more accessible than ever, with a wealth of incredible resources waiting for anyone with an internet connection and a sense of wonder. Let's start with the power of the written word. For a breathtaking, narrative-driven history of the entire quest to understand the cosmos, from the Big Bang to the CMB, you cannot do better than Big Bang by Simon Singh. It reads like a detective story, with a cosmic microwave background serving as the ultimate piece of forensic evidence. If you're ready to dive into the mind of a true visionary, The First 3 Minutes by Nobel laureate Steven Weinberg, while a bit more technical, remains a masterpiece that walks you through the physics of the universe's infancy with stunning clarity. And for the most up-to-date and engaging exploration of the very anomalies we've been discussing, including dark energy and the multiverse, The Edge of the Universe by award-winning science writer Paul Halpern is a fantastic and engaging tour of cosmology's greatest mysteries. For those who learn best through visual storytelling, the documentary world has you covered. The classic PBS Nova episode, At the Edge of Space and Time, which followed the development of the Planck mission, is a thrilling look at the immense human and technological effort behind these discoveries. For a broader, more philosophical journey, Brian Greene's The Fabric of the Cosmos miniseries, based on his book, does a beautiful job of explaining complex concepts like inflation and the nature of spacetime with cutting-edge graphics and relatable analogies. And of course, the YouTube channel Veritasium has several deeply researched and brilliantly explained episodes delving into the Big Bang and related topics, perfect for satisfying that immediate curiosity with high-quality, digestible content. But why just watch or read when you can actually do the science? This is where your journey can become truly active. The European Space Agency, which operated the Planck satellite, maintains a magnificent public archive where anyone can download the actual data that scientists use. With a bit of free software like the HealP package for Python, you can learn to process this data and create your own full sky maps of the cosmic microwave background. Imagine zooming in on the cold spot yourself, adjusting the contrast to see the subtle temperature variations, and truly appreciating the data that fuels these cosmic debates. For a more guided experience, platforms like Coursera and edX offer fantastic introductory courses on cosmology and astronomy from top universities like Caltech and Australian National University. These courses often include interactive modules where you can play with the parameters of the universe, tweak the amount of dark matter or dark energy, and see in real time how it would change the pattern of the CMB, giving you an intuitive feel for how cosmologists test their models. This hands-on engagement transforms you from a passive observer into an active participant in the greatest story ever told, fostering a deeper understanding that goes far beyond memorizing facts. It cultivates the most important tool in any scientist's kit, professional or amateur, a mindset of critical thinking and lifelong learning, empowering you to not just accept discoveries but to understand the evidence behind them. To truly understand the soul behind the data, you have to listen to the people who have devoted their lives to reading this cosmic story. I had the privilege of speaking with Professor Hiranya Paris, a leading cosmologist who was deeply involved in the Wilkinson microwave anisotropy probe team, and her perspective brings this entire endeavor into a beautifully human focus. She described the moment the first WMAP data streamed in not as a dry, technical event, but as a moment of profound, almost spiritual revelation. "There's a visceral thrill," she told me, "in seeing a pattern on your screen that you know has been traveling through the void for over 13 billion years, carrying the imprint of a universe 1,000 times smaller than a proton. You are the first consciousness in history to witness it. That never gets old." This sense of awe is the engine that drives researchers through years of painstaking, often frustrating work. But for every moment of awe, there are 1,000 moments of grueling skepticism. Professor George Efstathiou, a pivotal figure in both the COB and Planck missions, shared a story that perfectly captures the intense, self-critical nature of this work. During the early analysis of Planck data, his team noticed a curious, faint pattern that seemed to ripple across the entire map. The immediate, tantalizing thought was that this could be the first hint of primordial gravitational waves. The atmosphere was electric, but Efstathiou, a veteran of cosmic false alarms, immediately enforced a lockdown on excitement. He insisted the team operate under the assumption that it was a systematic error, an artifact of their own instrument. For weeks, they tore their own methodology apart, searching for any possible flaw, and they found it: a subtle, almost imperceptible effect from the way the satellite's cryogenic cooling system interacted with its sensors was creating a minute-repeating signal. The disappointment was palpable, but it was overshadowed by a greater emotion: pride. Pride in a process that prioritizes truth over triumph. As Efstathiou put it, "The easiest person to fool is yourself." Our job is to be our own most ruthless critics. This internal culture of brutal honesty is the bedrock of credibility in cosmology. This collaborative spirit extends far beyond any single team. Paris emphasized that modern CMB science is impossible without a kind of radical international cooperation that the world could learn from. The Planck satellite, for instance, wasn't just a European Space Agency project. Its data was analyzed by a consortium of hundreds of scientists from dozens of countries, each bringing their unique expertise to the table. She recounted late-night video conferences with colleagues in Japan, France, and the United States, all staring at the same cryptic plot on their screens, arguing in a mix of broken English and the universal language of mathematics. You have phenomenologists, string theorists, data modelers, and instrumentalists, she said. We all speak slightly different dialects. The breakthrough often comes when someone from a completely different field looks at your problem and says, "Well, have you tried thinking about it like this?" This cross-pollination of ideas is how the most stubborn problems get solved, proving that the universe's secrets are too complex for any one mind or any one nation to unravel alone. When I asked them about the future, specifically about the persistent anomalies, their answers were a masterclass in balanced scientific thinking. Neither dismissed them outright, nor did they proclaim a revolution. Efstathiou views them with a healthy, cautious intrigue. "The cold spot is interesting," he admitted, "but the evidence for a supervoid in that direction is mounting." Extraordinary claims require not just extraordinary evidence, but a complete exhaustion of ordinary explanations. We are not there yet. Paris, however, leans into the mystery with a different energy. She agrees that most anomalies will likely fade with better data, but she hopes one or two won't. We should almost be worried if everything fits perfectly, she said with a laugh. A completely clean, anomaly-free universe would suggest our model is right, but it might also mean we've stopped asking the most interesting questions. It's the tensions, the little cracks and wrinkles that force us to grow. They are the universe's way of telling us we're not done yet. This duality, Efthathiu's guardian of rigor and Paris's champion of curiosity, is not a contradiction. It is the essential dynamic tension that drives science forward. Their greatest hope lies not with their own generation, but with the next. Both scientists spoke passionately about the young PhD students and postdocs now leading the charge on projects like the Simons Observatory. These are the researchers who will have to live with the consequences of today's tantalizing hints. They are the ones who will get to work with data of such unimaginable precision that it will finally break the deadlock on inflation, dark matter, and the Hubble tension. Paris imagines them having the same eureka moments she did, but armed with tools she could only dream of. We are handing them the keys to the universe, Efthathiu concluded. We've given them a solid foundation, a few intriguing puzzles, and a set of instruments that are basically time machines. It is the most exciting time in human history to be a cosmologist. This passing of the torch, this shared commitment to a truth that is larger than any individual, is the real story of the cosmic microwave background. It is a human story written in the language of mathematics, etched onto the sky, and driven by a collective, enduring passion to understand our place in the grand cosmic narrative. Now, amidst all this thrilling talk of anomalies and new physics, it's absolutely crucial that we pause and clear the air of some very common and persistent misconceptions about the cosmic microwave background. When a scientific concept captures the public imagination the way the CMB has, it's almost inevitable that simplified explanations can become distorted, turning into myths that are often repeated as fact. So let's play a little cosmic myth busters and set the record straight on a few key ideas, because a clear understanding is the foundation of true wonder. Perhaps the most widespread myth is the idea that the cosmic microwave background radiation marks the actual, physical edge of the universe. This is a completely understandable mix-up, but it's fundamentally incorrect. The CMB is not a distant wall or a barrier at the end of space. Instead, think of it as the ultimate cosmic fog lifting. Imagine you're standing in the middle of an incredibly dense, foggy forest. You can only see a few feet in any direction. That's the universe before 380,000 years after the Big Bang, opaque and blinding. Then, suddenly, the fog lifts everywhere at once. You can now see trees much farther away, but the most distant trees you can see aren't the edge of the forest. They are simply the farthest trees whose light has had time to reach your eyes since the fog cleared. The CMB is that moment of the fog lifting, frozen in time. The light from that event has been traveling toward us for 13.8 billion years. We see it as a sphere all around us, not because it's a barrier, but because we are at the center of our own observable universe. The true, full universe is almost certainly vastly larger than what we can see, and it may indeed be infinite. The CMB is just the oldest light that has had time to reach us, the ultimate visual horizon, not a cosmic brick wall. Another powerful and related misconception is that if we could just build a telescope powerful enough, we could peer past the CMB and see what happened before it. This, unfortunately, is a physical impossibility. The era before the CMB is often called the Dark Ages of the universe for a very literal reason. It was truly dark. Not dark as in a starless night, but dark as in light could not travel freely. The universe was a searing, opaque plasma, a thick soup of particles where photons were constantly bouncing around, trapped. This means there are no photons from that earlier time that can reach us. Their journey would have been impossibly short before they were absorbed again. The CMB is the very first snapshot where the universe became transparent. Trying to see before the CMB would be like trying to use a camera to photograph a room before the light was ever turned on. There is simply no information, no light from that time available for us to capture. It is a fundamental curtain drawn across the very earliest chapters of cosmic history, and while we can use physics to theorize about what came before, we can never directly observe it with light. Then there's the more subtle but equally important myth that these strange anomalies we've been discussing, the cold spot, the axis of evil, somehow prove the Big Bang theory is wrong or in crisis. This misunderstands the very nature of scientific progress. The Big Bang theory is not a single, fragile idea. It's a robust framework that has been confirmed by multiple, independent lines of evidence, from the abundance of light elements to the observed expansion of the universe and the very existence of the CMB itself. These anomalies do not overthrow this framework. Instead, they are like finding a few unexpected and puzzling details in an otherwise perfectly verified historical document. They don't mean the entire history book is a forgery. They suggest that there might be more to the story, a subplot we hadn't appreciated. A good theory is not one that explains every single observation perfectly on the first try. A good theory is one that is precise enough to reveal its own shortcomings, to show us where the next layer of complexity lies. The anomalies are not the death knell of the Big Bang. They are the signposts pointing toward a deeper, richer version of it, one that likely includes inflation and perhaps physics we haven't even dreamed of yet. They are evidence that the model is alive and evolving, not that it is broken. Finally, let's tackle a misconception born from the name itself, that the cosmic microwave background is a form of interference or static we have to eliminate to see the real universe. This couldn't be further from the truth. It's not noise, it is the signal. It is the most important message we have. Radio astronomers working on communication signals might see the CMB as a frustrating background hiss they need to filter out, but for cosmologists, that hiss is the broadcast. Every satellite dish on Earth, every radio telescope, is constantly bathed in this light. It is not an obstacle to be overcome, but the treasure we are trying to mine for information. The entire field of cosmology is built on the idea of carefully, painstakingly listening to this specific static and decoding its incredibly subtle variations. The map of the CMB isn't what's left after we remove the noise. The map is made from the noise. This shift in perspective is everything. It transforms the CMB from a technical footnote into the main event, the oldest story ever told, waiting in the faintest whisper of microwave radiation for anyone patient and clever enough to listen. But perhaps the most profound philosophical implication of the cosmic microwave background lies in the stunning precision of its properties, which forces us to confront one of the most controversial and mind-bending ideas in all of science, the anthropic principle. This concept emerges from a simple yet staggering observation. The fundamental constants and conditions of our universe appear to be exquisitely, almost impossibly, fine-tuned for the existence of life. If the force of gravity were even slightly stronger, the universe would have collapsed back on itself long before stars could form. If it were slightly weaker, matter would never have clumped together into galaxies. If the strength of the nuclear force were different by a mere fraction of a percent, stars would be unable to forge the carbon and oxygen that are the building blocks of life as we know it. This list of cosmic coincidences is long and deeply unsettling. It creates the powerful impression that the universe was somehow designed or calibrated with us in mind. This is where the CMB becomes the central piece of evidence, that moment of recombination, frozen in time within the microwave static, was the ultimate fine-tuning event. The initial strength of the primordial fluctuations, so precisely measured by Planck, was absolutely critical. If those quantum seeds had been just a little bit stronger, the universe would have collapsed into a nightmare landscape of giant black holes far too early for planets to form. If they had been a little bit weaker, the gravitational pull would have been too feeble to gather matter into galaxies and stars at all. The cosmos would have remained a forever thin, dark, and lifeless haze of hydrogen. The fact that we exist to observe a CMB with its specific, life-permitting pattern of fluctuations is, according to the anthropic principle, not a coincidence. It is a selection effect. In a very real sense, the universe we observe must have properties that allow observers to exist, because if it didn't, we wouldn't be here to see it. This line of reasoning, while logically sound, makes many scientists deeply uncomfortable because it can feel like a conversation stopper, a way of avoiding a deeper physical explanation. But it also opens the door to a spectacularly grand possibility, the multiverse. If our universe is just one of a vast, perhaps infinite, number of universes, each with its own randomly selected set of physical constants and laws, then the mystery of fine-tuning vanishes. In an infinite multiverse, every possible combination of physical parameters will be realized somewhere. We inevitably find ourselves in one of the rare, bio-friendly universes because those are the only ones where life can arise to ponder the question. The cosmic microwave background in this context is not a unique message from a singular creation event, but simply our local weather report. Its specific temperature, its fluctuation spectrum, and even its puzzling anomalies like the cold spot or the axis of evil might not be fundamental features of reality. They might just be the local bylaws of our particular cosmic neighborhood, a random draw from a limitless lottery of possibilities. This idea pushes the conversation to the very boundaries of science and philosophy. It forces us to ask what, if anything, can be considered a genuine scientific explanation. A theory that predicts everything predicts nothing. If the multiverse can accommodate any possible observation, does it have any real explanatory power? Proponents argue that it does, but only if it makes specific, testable predictions. They suggest that if our universe is indeed one bubble in a frothing multiverse, then the regions where bubbles collide might leave imprints on the CMB-specific, circular patterns of temperature variation. The ongoing, fruitless search for such signatures in the Planck data is a genuine attempt to find empirical evidence for this breathtaking idea. Furthermore, some versions of the multiverse predict that certain types of anomalies should be more common in life-permitting universes. Could the large-scale asymmetry we see be a statistical hallmark of our particular type of bio-friendly bubble? It's a profoundly speculative thought, but it demonstrates how the anthropic principle can be more than just a philosophical shrug. It can guide a physical research program, using the detailed map of the CMB as a testing ground for the ultimate nature of reality. Ultimately, the cosmic microwave background holds up a mirror, and what we see reflected back is a choice about how we understand our place in the cosmos. One view is teleological, seeing the precise numbers encoded in the CMB as evidence for a deeper purpose or design, a universe that was somehow meant to be. The other view is radically existential. It suggests we are the product of unimaginable chance, living in a universe that is utterly indifferent to our existence. one that just happens to have the right conditions by pure, mind-numbing luck. The CMB doesn't tell us which of these perspectives is correct. Its silent microwave whisper simply presents us with the data, a universe that is, against all odds, perfectly suited for us. How we choose to interpret that astonishing fact as a miracle, a coincidence, or a selection bias in an infinite reality remains one of the most profound questions we can ask ourselves. It is the point where our most precise science dissolves into the deepest wonder, leaving us humbled by the sheer unlikeliness of our own existence. The quest to decode the universe's oldest light is a testament to a profound truth: the cosmos knows no borders. Unlike the grand astronomical observatories of the past, built by lone nations in a spirit of competition, the study of the cosmic microwave background has, from its very beginning, been a symphony of global collaboration. This isn't a field where one country can hoard the data or claim sole ownership of a discovery. The scale of the challenge is simply too vast, the required expertise too diverse, and the necessary perspectives too varied for any single entity to succeed alone. To map the faint whisper of creation requires a united front of human ingenuity, a merging of minds and resources from across the planet, all focused on a single, shared goal. This incredible endeavor transforms remote, inhospitable corners of our world into bustling international hubs of discovery, where the harsh silence of the polar ice or the thin air of high-altitude deserts is filled with the hum of machinery and the shared language of science. Consider the iconic locations that have become the front line in this cosmic census. The South Pole is one of the most extreme environments on Earth, a frozen desert where temperatures can plummet to negative 80 degrees Celsius and the sun doesn't rise for 6 months of the year. It is also, paradoxically, one of the best places on the planet to observe the cosmos. The air is incredibly dry, stable, and pristine, free from the water vapor and atmospheric turbulence that plague more temperate latitudes. Here, at the very bottom of the world, you will find the BICEP and Keck array telescopes, a series of instruments that have been tirelessly scanning the sky for the faint swirls of primordial gravitational waves. The team that operates and maintains these instruments is never from just one institution or one country. A typical winter-over crew might include an engineer from Caltech, a data specialist from the University of Minnesota, and a telescope operator from Harvard-Smithsonian, all living and working in tight quarters at the Amundsen Scott South Pole Station, a place so remote that it is completely cut off from the outside world for the long, dark winter months. Their collaboration is a matter of survival as much as science, a bond forged in the shared experience of isolation and the pursuit of a common, transcendent objective. Similarly, the high, dry plateaus of the Atacama Desert in Chile have become a cosmic crossroads. The altitude, over 5,000 meters above sea level, places observers above a significant portion of Earth's atmosphere, while the arid conditions minimize the interfering glow of water vapor. This is the home of the Atacama Cosmology telescope and the future site of the massive Simons Observatory. Building and operating these facilities is a logistical ballet performed by an international consortium. The telescope components might be designed in the United States, fabricated with precision in Germany, assembled by a team of engineers from Canada and the UK, and installed on the mountain by Chilean technicians who possess invaluable local knowledge of the environment. This isn't just about sharing costs, though that is a significant benefit. It is about pooling a global reservoir of specialized talent. A problem with a cryogenic cooler might be solved by a video call with an expert in Japan, while a tricky statistical analysis of the data is crowdsourced to a team of cosmologists in Italy and South Africa. The project becomes a living entity, its heartbeat a constant around-the-clock flow of emails, code, and ideas across every time zone. The benefits of this model extend far beyond the practical. There is an immense intellectual advantage to integrating such wildly diverse perspectives. A cosmologist trained in the theoretical traditions of India might approach a data analysis problem from a completely different angle than a colleague from France, leading to a novel solution that neither would have conceived of alone. A junior researcher from Nigeria, brought into the collaboration through a dedicated inclusion program, might spot a systematic error in the data processing that more senior scientists had overlooked because they were too close to the project. This cross-pollination of ideas is the engine of innovation. It acts as a built-in system of peer review, where assumptions are constantly challenged and methodologies are refined through a crucible of international scrutiny. The final published paper from a project like Planck had over 1,000 authors from more than 100 institutions worldwide. That staggering list of names isn't just a formality. It is an accurate reflection of the collective effort required to turn raw data into cosmological insight. It represents the countless hours of discussion, debate, and shared problem-solving that turned individual expertise into a unified, monumental achievement. Of course, this grand collaboration is not without its significant challenges. Melding different scientific cultures, funding agency rules, and even workday schedules across continents requires a monumental effort in diplomacy and project management. Data ownership and authorial credit can become delicate issues that require carefully crafted international agreements long before the first bolt is turned. The physical act of shipping delicate, one-of-a-kind equipment from a laboratory in Princeton to a mountaintop in Chile is a nerve-wracking ordeal, with customs forms and import regulations posing as great a threat to the project as any technical glitch. Communication barriers, both linguistic and cultural, must be patiently overcome. Yet, the scientists who lead these efforts universally report that the rewards far outweigh the headaches. They describe a unique sense of shared purpose that transcends nationality, a feeling that they are working not for the glory of their home country, but for the advancement of all humanity. In an era often marked by division and competition, the global study of the cosmic microwave background stands as a powerful, enduring example of what we can achieve when we choose to look up at the same sky and work together to understand our common origin. The map of the infant universe we are piecing together is not an American map or a European map or a Chinese map. It is a human map, a testament to our species' unique ability to cooperate on a global scale in the pursuit of pure knowledge, a collective achievement that belongs to everyone on the planet it so beautifully depicts. So as we reach the end of our journey from a noisy antenna in New Jersey to the edge of the observable universe and beyond, what have we truly learned? The story of the cosmic microwave background is not one of a mystery solved, but of a mystery that grows richer and more profound with every new layer we uncover. We began with a nearly perfect blackbody spectrum, a testament to a simple, hot beginning. We then discovered the tiny ripples that seeded all of existence, a triumphant confirmation of our most elegant models. But with greater precision came greater complexity, the cold spot, the axis of evil, the Hubble tension anomalies that refuse to be smoothed away, whispers from the dawn of time that suggest our map of the cosmos is still missing crucial and perhaps breathtaking details. This is not a failure of science, it is its greatest success. A perfect, complete theory would be a dead end. These puzzles are the signposts pointing us toward the next great leap in understanding. This endless cycle of discovery and refinement is the very heartbeat of the scientific endeavor. Each generation builds upon the tools of the last, from Penzias and Wilson's humble horn to Planck's exquisite orbital observatory. each instrument revealing a universe more complex and wondrous than we had previously imagined. And just as we master one set of clues, the cosmos presents us with another, reminding us that the pursuit of knowledge is a perpetual journey, not a destination with a final flag to be planted. We are like explorers who have finally reached a long-sought coastline, only to realize it is merely the shore of a continent vaster and more mysterious than we ever dreamed. The questions we ask today will seem elementary to the Chinese letter of scientists armed with the data from CMB S4 and Light Bird, who will in turn be humbled by the new and deeper mysteries their discoveries will inevitably reveal. This grand quest does more than just satisfy our curiosity. It fundamentally changes our relationship with the cosmos and with ourselves. It reminds us that we are not passive observers of a static universe, but active participants in an unfolding story of discovery. The atoms that form our bodies were forged in the hearts of ancient stars, and the light from the universe's infancy is falling upon us at this very moment. We are, in the most literal sense, the universe become conscious, able to look back upon its own origins and ask how it came to be. This connects us to every human who has ever looked up at the night sky in wonder, and to every future generation that will continue the search. As Carl Sagan so beautifully put it, the cosmos is within us. We are made of star stuff. We are a way for the universe to know itself. This is the true power of the cosmic microwave background. It is not just a fossil to be studied, but a mirror in which we see our own origins reflected. Now we want to hear from you. This story is far from over, and the next chapter is being written by a global community of curious minds. Which of these cosmic anomalies captures your imagination the most? Does the sheer scale of the cold spot make you wonder about collisions with other universes? Does the philosophical defiance of the axis of evil unsettle your view of a perfectly random cosmos? Or does the stubborn practicality of the Hubble tension excite you the most, as it promises new physics hiding just beyond our current equations? Share your thoughts in the comments below. Let's continue this conversation together. Your wonder and your questions are the most important tools we have, because they ensure that the journey of discovery will never truly end. Thank you for joining us on this exploration of the oldest light in the universe. And remember, no matter how much we learn, there will always be more to discover just over the next